The sun, a fiery cosmic giant. Imagine standing on a beach, feeling the warmth of sunlight on your skin. That gentle heat has traveled nearly 93 million miles through the cold void of space to reach you. It comes from the sun, a massive ball of fire and energy that powers our solar system and makes life on Earth possible. This glowing sphere is not just a distant star, it's a dynamic force shaping everything around us. At its core, the sun is a nuclear furnace where hydrogen atoms fuse together to form helium, releasing an unimaginable amount of energy in the process. Every second, the sun converts about 600 million tons of hydrogen into helium. To put this into perspective, if we could harness even a fraction of the energy produced by the sun in 1 second, it would power all human activity for thousands of years. This constant fusion reaction generates temperatures at the sun's core exceeding 27 million degrees Fahrenheit, which is equivalent to 15 million degrees Celsius, hotter than anything we can create here on Earth. The surface of the sun, known as the photosphere, might seem cooler compared to its fiery interior, but don't be fooled. It still burns at 10,000 degrees Fahrenheit or 5,500 degrees Celsius. From this layer, light escapes into space, bathing planets, moons, and asteroids with radiant energy. But the sun isn't static. It's alive with motion. Towering loops of plasma called solar prominences arch outward, stretching hundreds of thousands of miles above the surface. These eruptions are driven by the sun's magnetic field, which twists and contorts like invisible threads pulling at molten iron. One of the most fascinating features of the sun is its ever-changing face. Dark patches known as sunspots appear when intense magnetic activity temporarily cools certain areas. Though they look small from afar, these spots are often larger than Earth itself, spanning tens of thousands of miles. Surrounding them are regions of heightened activity, where flares and coronal mass ejections burst forth. When these powerful bursts of charged particles collide with Earth's atmosphere, they create stunning displays of light called auroras, painting the night sky in shimmering greens, pinks, and purples. The sun also plays a critical role in maintaining balance within the solar system. Its immense gravitational pull keeps planets, including ours, in orbit, preventing them from drifting off into deep space. Without the sun's steady influence, Earth would spiral away into darkness, freezing over as temperatures plummeted to minus 400 degrees Fahrenheit or minus 240 degrees Celsius. Even the length of our days and seasons depends on the sun's position relative to Earth. As our planet tilts on its axis while orbiting the sun, different hemispheres receive varying amounts of sunlight throughout the year, giving rise to spring, summer, autumn, and winter. Despite its brilliance, the sun is not eternal. Like all stars, it follows a life cycle. Right now, it's classified as a main sequence star, meaning it's in the prime of its life. However, in roughly 5 billion years, the sun will run out of hydrogen fuel in its core. When that happens, it will expand dramatically, swallowing Mercury and Venus, and possibly Earth, before shedding its outer layers and collapsing into a white dwarf. For now, though, we can marvel at its enduring presence, knowing that it has billions of years left to shine. Every time you step outside and feel the sun's rays, remember that you're experiencing the product of processes occurring millions of miles away. This fiery cosmic giant may seem distant, yet it shapes every moment of our lives, providing the energy needed for plants to grow, winds to blow, and oceans to ripple. In many ways, the sun is both the heart and the engine of our solar system, a reminder of how interconnected everything truly is. To better understand the sun's scale, consider this. If the sun were hollow, over 1 million Earths could fit inside it. Its diameter stretches 864,000 miles, or 1.4 million kilometers, making it more than 100 times wider than our planet. Yet despite its size, the sun is surprisingly lightweight compared to its volume. Its density is so low that if you could somehow scoop out a chunk of the sun and bring it back to Earth, it would float in water. This combination of mass and size creates a delicate equilibrium that allows the sun to burn steadily without collapsing under its own weight or exploding outward. The sun's energy doesn't stop at visible light. It emits radiation across the entire electromagnetic spectrum, including ultraviolet rays, X-rays, and radio waves. While some of this energy is harmful to living organisms, Earth's atmosphere acts as a protective shield, filtering out dangerous wavelengths while allowing beneficial ones to pass through. For example, ultraviolet light helps our bodies produce vitamin D, essential for bone health. At the same time, ozone in the upper atmosphere absorbs excess UV radiation, protecting us from its damaging effects. Another intriguing aspect of the sun is its magnetic personality. The sun's magnetic field flips approximately every 11 years, a phenomenon known as the solar cycle. During periods of high activity, known as solar maximum, the sun produces more sunspots, flares, and coronal mass ejections. Conversely, during solar minimum, activity slows down, leading to fewer disturbances in space weather. These cycles have profound implications for Earth. Increased solar activity can disrupt satellite communications, interfere with GPS signals, and even cause power grid failures. On the other hand, periods of calm allow scientists to study the sun's quieter behaviors, such as subtle changes in its brightness. The sun's influence extends far beyond what we see in the daytime sky. Its solar wind, a stream of charged particles flowing outward at speeds up to 1,000,000 miles per hour, creates a vast bubble around the solar system known as the heliosphere. This protective barrier shields planets from harmful cosmic rays originating in interstellar space. Without the heliosphere, Earth would be bombarded by high-energy particles capable of stripping away our atmosphere and endangering life. The Voyager spacecraft, launched in the 1970s, recently crossed the boundary of the heliosphere, entering interstellar space for the first time in history. Data from these probes has revealed new insights into how the sun interacts with its surroundings. For centuries, humans have looked to the sun as a symbol of power, vitality, and renewal. Ancient civilizations built monuments aligned with its movements, tracking solstices and equinoxes to mark the passage of time. Today, modern technology allows us to study the sun in unprecedented detail. Telescopes like NASA's Solar Dynamics Observatory capture high-resolution images of the sun's surface, revealing intricate patterns of plasma swirling across its face. Meanwhile, missions like the Parker Solar Probe are venturing closer to the sun than ever before, braving extreme temperatures of up to 2,500 degrees Fahrenheit or 1,377 degrees Celsius to unlock its deepest secrets. Understanding the sun is not just an academic pursuit, it's vital for humanity's future. As we develop technologies to harness solar energy, we reduce our reliance on fossil fuels and combat climate change. Solar panels convert sunlight directly into electricity, offering a clean and renewable source of power. In addition, studying the sun helps us prepare for potential hazards like solar storms, which could cripple infrastructure if left unchecked. By learning more about this fiery giant, we gain tools to protect ourselves and build a sustainable world. The sun's story is one of transformation and endurance. Born from a cloud of gas and dust, billions of years ago, it has grown into the dominant force in our corner of the universe. Its light illuminates the darkest corners of space, guiding explorers and dreamers alike. And though it will eventually fade, its legacy will endure in the elements, forged within its core, scattered across the cosmos to seed new stars, planets, and perhaps even life itself. As you gaze upward at the golden orb hanging in the sky, take a moment to appreciate its complexity and beauty. The sun is more than just a source of warmth and light. It's a testament to the wonders of the universe and our place within it. Through its ceaseless energy and unyielding presence, the sun reminds us of the delicate balance that sustains existence and inspires us to explore the mysteries of the cosmos. Mercury, a world of extremes. Mercury is a planet of contradictions, a place where the sun looms 3 times larger in the sky than it does on Earth, yet its surface remains one of the most desolate and unforgiving environments imaginable. This tiny world, orbiting closest to our star, is a study in extremes, blisteringly hot during the day and bone-chillingly cold at night. It's a planet that defies expectations and challenges everything we think we know about habitability. Mercury's proximity to the Sun gives it the shortest year of any planet in the solar system, completing an orbit in just 88 Earth days. Yet despite its rapid journey around the Sun, Mercury spins incredibly slowly on its axis. A single day on Mercury lasts 59 Earth days, meaning that one Mercurian day stretches across nearly 2 Mercurian years. This unusual relationship between its rotation and orbit creates some of the most dramatic temperature swings in the solar system. During the day, temperatures on Mercury soar to 800 degrees Fahrenheit or 430 degrees Celsius, hot enough to melt lead. But as soon as the sun dips below the horizon, the lack of atmosphere means there's nothing to trap heat. Nighttime temperatures plummet to minus 290 degrees Fahrenheit or minus 180 degrees Celsius, colder than the coldest places on Earth. These wild fluctuations make Mercury a world of constant transformation, where every sunrise brings searing heat and every sunset plunges the surface into icy darkness. Mercury's barren landscape resembles Earth's moon, covered in craters from billions of years of impacts by asteroids and comets. One of its most striking features is the Calorus Basin, a massive impact crater stretching nearly 1,000 miles across, or roughly the size of Texas. The force of the collision that created this basin was so immense that it sent shockwaves rippling through the planet, leaving chaotic terrain on the opposite side. These scars tell the story of Mercury's violent past, a testament to the chaos of the early solar system. Despite its harsh conditions, Mercury holds secrets that continue to intrigue scientists. Beneath its scorched surface lies evidence of ancient volcanic activity. Lava flows once filled many of the planet's craters, smoothing them over and creating vast plains. While these eruptions likely ceased billions of years ago, their remnants hint at a time when Mercury was geologically alive. Even today, subtle shifts in the planet's crust suggest that it may still be cooling and contracting ever so slightly, causing small faults and ridges to form on its surface. One of the most surprising discoveries about Mercury came from NASA's Messenger spacecraft, which orbited the planet between 2011 and 2015. Scientists found evidence of water ice hidden in the shadows of craters near Mercury's poles. These permanently shadowed regions never see sunlight, allowing ice to persist despite the planet's scorching temperatures elsewhere. How did water end up on such an inhospitable world? The leading theory suggests that comets and meteorites delivered the ice during collisions, depositing it in areas where it could survive for eons. Mercury's small size and close proximity to the Sun have also shaped its gravity and structure. With a diameter of just 3,032 miles, or 4,880 kilometers, Mercury is only slightly larger than Earth's moon. Its weak gravity means it can't hold on to an atmosphere like Earth's. Instead, it has an exceedingly thin exosphere, made up of atoms blasted off the surface by solar wind and micrometeorite impacts. This sparse veil of particles drifts away into space, constantly replenished by external forces. The Sun dominates Mercury's sky, appearing far brighter and more intense than it does from Earth. Because of Mercury's elliptical orbit, the apparent size of the Sun changes dramatically throughout the year. At perihelion, when Mercury is closest to the Sun, our star appears twice as large as it does at aphelion, when the planet is farthest away. This shifting perspective underscores the dynamic nature of Mercury's environment, where even the heavens themselves seem restless. Exploring Mercury poses unique challenges for scientists and engineers. The extreme temperatures and intense solar radiation make it difficult to design spacecraft capable of surviving long-term missions. Yet the rewards are worth the effort. Studying Mercury helps us understand the formation of rocky planets, including Earth, and provides clues about the early solar system. For example, Mercury's unusually large iron core, about 85% of its radius, suggests that it may have once been part of a much larger planet that lost its outer layers in a catastrophic collision. Mercury's stark beauty lies in its simplicity. There are no clouds, no oceans, and no signs of life. What you see is what you get. A raw, unfiltered glimpse into the fundamental processes that shape worlds. Its surface tells a story written in dust and rock, a narrative of survival against overwhelming odds. Each crater, each ridge, and each patch of shadowed ice speaks to the resilience of matter in the face of unimaginable forces. As we peer closer at Mercury, we're reminded of the delicate balance that allows life to thrive on Earth. Our planet's thick atmosphere, moderate temperatures, and protective magnetic field shield us from the kinds of extremes that define Mercury. In studying this alien world, we gain a deeper appreciation for the rare and precious conditions that sustain us. Mercury may be a world of extremes, but it's also a teacher. It shows us the power of the sun, the fragility of atmospheres, and the enduring legacy of cosmic collisions. Though it lacks the vibrant colors of Mars or the swirling storms of Jupiter, Mercury captivates us with its stark honesty. It reminds us that even in the harshest corners of the solar system, there is wonder waiting to be discovered. And so, as we turn our gaze back toward the innermost planet, we carry with us not just knowledge but awe. Mercury's silence speaks volumes, whispering tales of fire and ice, chaos and calm, destruction and endurance. It is a world unlike any other, a testament to the infinite variety of the universe and our endless quest to understand it. Venus, Earth's toxic twin. Venus often earns the nickname Earth's twin because of its similar size, mass, and composition. But don't let that fool you. This planet is anything but hospitable. Beneath its thick veil of clouds lies a world of crushing pressures, searing temperatures, and an atmosphere so toxic it could kill in seconds. Venus may resemble Earth from afar, but up close, it's a vision of planetary hell, a cautionary tale about what can happen when a world spirals out of balance. At first glance, Venus seems like it could be Earth's long-lost sibling. It's roughly 7,520 miles in diameter, just slightly smaller than Earth, and its gravity is about 90% as strong, but the similarities end there. Venus is shrouded in a dense layer of clouds made primarily of sulfuric acid, reflecting sunlight so brightly that it's often mistaken for a star, the morning or evening star, by early astronomers. These clouds hide a surface so hostile that no spacecraft has survived on it for more than a few hours. The most striking difference between Venus and Earth is its runaway greenhouse effect. Venus's atmosphere is composed almost entirely of carbon dioxide, with traces of nitrogen and other gases. This thick blanket traps heat with devastating efficiency, raising surface temperatures to a staggering 864 degrees Fahrenheit or 462 degrees Celsius, hot enough to melt lead. For comparison, that's hotter than the hottest ovens on Earth and even exceeds the temperature of Mercury, despite Venus being farther from the sun. If you were to step onto Venus's surface, the heat would overwhelm you instantly, making survival impossible without advanced protection. But the heat isn't the only danger. The atmospheric pressure on Venus is over 90 times greater than Earth's at sea level, equivalent to the pressure found nearly half a mile beneath Earth's oceans. This oppressive weight would crush most machines, and humans like an empty soda can. Early Soviet probes sent to explore Venus, such as the Venera series, managed to transmit data and images for mere minutes before succumbing to the planet's brutal conditions. Those haunting black and white photos revealed a barren, rocky landscape littered with sharp-edged boulders and flat plains, all bathed in an eerie orange glow caused by the filtered sunlight struggling to penetrate the thick clouds above. Venus's bizarre rotation adds another layer of strangeness to this enigmatic world. Unlike most planets, Venus rotates backward, or retrograde, meaning the sun rises in the west and sets in the east. What's more, a single day on Venus lasts longer than a year. One full rotation takes 243 Earth days, while one orbit around the Sun takes only 225 Earth days. This means that a day on Venus lasts longer than its entire year, creating a surreal rhythm unlike anything we experience on Earth. Despite its harsh environment, Venus wasn't always a fiery wasteland. Scientists believe that billions of years ago, Venus might have had a milder climate, perhaps even liquid water oceans. Evidence suggests that during its early history, Venus may have been cool enough for water to exist in liquid form, potentially fostering conditions favorable for life. However, something catastrophic tipped the scales. A combination of factors, such as volcanic activity releasing massive amounts of carbon dioxide, the loss of any magnetic field to protect against solar wind, and the gradual evaporation of water into space, likely triggered a feedback loop that turned Venus into the inferno we see today. Its transformation serves as a stark reminder of how delicate planetary climates can be. One of Venus's most fascinating features is its global weather system. High above the surface, winds race around the planet at speeds exceeding 220 miles per hour, or 350 kilometers per hour, faster than the planet itself rotates. These super-rotating winds create a chaotic upper atmosphere, where sulfuric acid droplets swirl in perpetual motion. Yet closer to the ground, the air moves sluggishly, adding to the planet's paradoxical nature. It's as if Venus exists in two different worlds stacked atop one another, a frenetic, fast-moving sky above and a slow, suffocating surface below. Exploring Venus has proven to be one of humanity's greatest challenges. The extreme temperatures and pressures make landing missions exceptionally difficult, and the corrosive atmosphere quickly destroys equipment. Despite these hurdles, scientists have pieced together a detailed picture of Venus using radar mapping from orbiting spacecraft like NASA's Magellan mission. These efforts revealed vast highland regions, deep valleys, and thousands of volcanoes dotting the surface. Some researchers speculate that Venus may still be geologically active, with lava flows reshaping parts of the planet even today. If true, this would mean Venus is not entirely dead. It's a dynamic world still undergoing change. Venus also holds lessons for understanding climate change here on Earth. Its runaway greenhouse effect provides a grim preview of what could happen if we fail to address rising carbon dioxide levels in our own atmosphere. While Earth benefits from natural systems that regulate greenhouse gases, Venus shows us what happens when those systems break down. Studying Venus helps scientists model potential futures for our planet and underscores the importance of protecting Earth's delicate equilibrium. For all its hostility, Venus remains a source of fascination and inspiration. Its golden-hued clouds and mysterious surface continue to captivate astronomers and dreamers alike. Though it may never host life as we know it, Venus reminds us of the incredible diversity of worlds within our solar system. It challenges us to think beyond the familiar and consider how environments vastly different from our own can still teach us valuable lessons. As we gaze toward Venus in the night sky, it appears serene and beautiful, a bright beacon among the stars. But beneath its tranquil exterior lies a world of extremes, a toxic twin that warns us of the fragility of habitable planets. Venus is a testament to the power of nature, a reminder that even planets once teetering on the edge of habitability can fall victim to their own instability. And yet, in its desolation, there is beauty, a stark, alien allure that draws us ever closer in our quest to understand the cosmos. Venus may not be a place we'll visit anytime soon, but its story resonates deeply. It speaks of beginnings and endings, of promise and peril, of the thin line between paradise and ruin. In studying Venus, we learn not only about another world, but also about ourselves and the responsibility we bear to safeguard the precious oasis we call home. Earth, the only living planet. In the vast expanse of the cosmos, there is one world that stands apart, a vibrant, dynamic sphere teeming with life, color, and complexity. Earth, our home, is a rare gem in the universe, a planet uniquely suited to support an astonishing diversity of organisms, from towering redwoods to microscopic bacteria. It's the only place we know where life exists, a delicate balance of forces that has allowed ecosystems to flourish for billions of years. But what makes Earth so special? And how does it sustain the intricate web of existence that defines it? From space, Earth appears as a swirling masterpiece of blues, greens, and whites. Its oceans shimmer like liquid sapphires, covering more than 70% of its surface. These vast waters are not just beautiful, they're essential to life. Oceans regulate the planet's temperature, store carbon dioxide, and provide habitats for countless species. Above them, clouds drift lazily across the sky, carrying moisture that feeds forests, grasslands, and cities alike. This interplay of water, air, and land creates a symphony of processes that keep Earth alive. At the heart of Earth's uniqueness lies its atmosphere, a thin but vital layer of gases enveloping the planet. Composed mostly of nitrogen and oxygen, this invisible shield does far more than allow us to breathe. It protects life from harmful ultraviolet radiation, moderates temperatures, and traps just enough heat through the greenhouse effect to prevent the planet from freezing. Without this protective cocoon, Earth would resemble its neighbors, Mars a cold desert, or Venus a scorching inferno. The atmosphere is a fragile gift, one that humanity must safeguard as we face the challenges of climate change. Earth's magnetic field adds another layer of protection, shielding the planet from solar wind and cosmic radiation. Generated deep within the core, where molten iron swirls in constant motion, this invisible force creates a barrier known as the magnetosphere. Without it, the atmosphere could be stripped away over time, leaving Earth vulnerable to the harsh conditions of space. This dynamic interaction between Earth's interior and exterior highlights the interconnectedness of the planet's systems, each playing a crucial role in maintaining the conditions necessary for life. The diversity of landscapes on Earth is breathtaking. Towering mountain ranges rise majestically above plains, their peaks often capped with snow. Rivers carve winding paths through valleys, shaping the land as they flow toward the sea. Deserts stretch endlessly under blazing suns, while rainforests burst with life in every shade of green. Each ecosystem contributes to the planet's overall health, supporting species adapted to specific environments. Coral reefs, for example, are often called the rainforests of the sea because of their incredible biodiversity, providing food, shelter, and breeding grounds for marine creatures. Life itself is Earth's greatest marvel. From the smallest microbe to the largest whale, every organism plays a part in the grand tapestry of existence. Plants harness sunlight through photosynthesis, converting it into energy and releasing oxygen as a byproduct. Animals, in turn, depend on plants for sustenance, creating a cycle that has sustained life for eons. Humans, too, are deeply embedded in this network, relying on Earth's resources for food, water, and shelter. Yet our relationship with the planet is complex. We have the power to nurture or harm, to protect or exploit. One of Earth's most remarkable features is its ability to adapt and recover. Over millions of years, the planet has endured ice ages, asteroid impacts, and volcanic eruptions, each event reshaping its surface and influencing the course of evolution. Life has persisted through it all, finding ways to survive even in the harshest conditions. Extremophiles, organisms that thrive in environments once thought uninhabitable, remind us of life's resilience. Whether clinging to hydrothermal vents on the ocean floor or surviving in acidic hot springs, these hardy beings expand our understanding of what's possible and perhaps hint at the potential for life elsewhere in the universe. Yet Earth's story is not without peril. Human activity has introduced new challenges, from deforestation and pollution to rising global temperatures. Climate change, driven by the burning of fossil fuels and the release of greenhouse gases, threatens to disrupt the delicate balance that sustains life. Glaciers are melting, sea levels are rising, and weather patterns are becoming increasingly erratic. These changes serve as urgent reminders of our responsibility to care for the planet. Earth has given us everything. Now it's up to us to ensure its future. Despite these challenges, there is hope. Around the world, people are working together to address environmental issues and promote sustainability. Renewable energy sources like solar and wind power are reducing reliance on fossil fuels. Conservation efforts are protecting endangered species and preserving natural habitats. Innovations in agriculture and technology are helping communities adapt to changing conditions. While the road ahead may be difficult, humanity's capacity for ingenuity and cooperation offers reason to believe we can create a brighter future. Earth's beauty extends beyond its physical attributes. It lies in its stories, its mysteries, and its endless capacity to inspire wonder. Every sunrise paints the horizon in hues of gold and pink, a daily reminder of the planet's vitality. Every storm brings thunder and lightning, raw displays of nature's power. Even the quiet moments, the rustle of leaves in a breeze, the lapping of waves against a shore, carry a profound sense of connection to something greater than ourselves. As we explore other worlds in search of life, Earth remains our ultimate reference point. It teaches us about the conditions needed to support living organisms and underscores the rarity of such a perfect alignment of factors. Water, energy, and stable climates are prerequisites for life as we know it, and Earth exemplifies how these elements can come together in harmony. Studying our planet helps scientists refine their search for extraterrestrial life, guiding missions to Mars, Europa, and beyond. But perhaps Earth's greatest lesson is one of gratitude. For all its complexity and fragility, this planet provides everything we need to survive and thrive. Its soil grows our food, its rivers quench our thirst, and its skies offer inspiration and solace. In return, we owe it our respect and stewardship. Earth is not just a backdrop for human history, it is an active participant shaping our past, present, and future. Earth is more than the only living planet. It is a living testament to the wonders of the universe. Its mountains, oceans, and skies tell a story billions of years in the making, a narrative of resilience, adaptation, and interconnectedness. As we continue to explore the cosmos, let us never forget the extraordinary world beneath our feet. It is a treasure worth protecting, a sanctuary worth cherishing, and a reminder of the boundless possibilities inherent in the fabric of existence. And so, as we gaze upward at the stars, let us also look inward toward the blue-green orb that cradles us all. Earth is not merely a stage for our adventures. It is the foundation of our being, the source of our strength, and the keeper of our dreams. In its embrace, we find purpose, belonging, and the courage to reach for the heavens. Mars, the red planet's secrets. Mars has long captured the human imagination, a distant world painted in shades of rust and ochre, its surface etched with scars that tell tales of a bygone era. Known as the Red Planet, Mars is a place of mystery and intrigue, a barren desert world that hints at a past far richer and more dynamic than its current state suggests. From ancient riverbeds to towering volcanoes, Mars holds secrets that could rewrite our understanding of planetary evolution and perhaps even answer one of humanity's most profound questions. Are we alone in the universe? At first glance, Mars appears desolate, its reddish hue caused by iron oxide or rust coating its dusty surface. But beneath this seemingly lifeless exterior lies evidence of a planet that was once vastly different. Billions of years ago, Mars may have had a thicker atmosphere, warmer temperatures, and liquid water flowing across its surface. Today, remnants of those ancient rivers, lakes, and deltas can still be seen, carved into the Martian terrain like ghostly fingerprints of a wetter, more hospitable past. These features suggest that Mars might have been capable of supporting life, microbial perhaps, but life nonetheless. One of the most striking landmarks on Mars is Olympus Mons, the largest volcano in the solar system. Standing nearly 14 miles high, or about 22 kilometers, it dwarfs Earth's tallest peak, Mount Everest. Olympus Mons stretches so wide that if you were standing at its base, its summit would disappear beyond the horizon due to the curvature of the planet. This colossal mountain is part of the Tharsis region, a volcanic plateau home to several other massive volcanoes. Their sheer size speaks to Mars's geological history. Unlike Earth, where tectonic plates shift and recycle the crust, Mars lacks plate tectonics. As a result, lava repeatedly erupted from the same spots over millions of years, building these enormous structures layer by layer. Another iconic feature of Mars is Valles Marineris, a canyon system so vast it makes Earth's Grand Canyon look like a mere crack in the ground. Stretching over 2,500 miles, or 4,000 kilometers, and reaching depths of up to 7 miles, or 11 kilometers, Valles Marineris spans nearly a quarter of the planet's circumference. Scientists believe it formed through a combination of tectonic activity and erosion, though its exact origins remain debated. Whatever the cause, this immense chasm offers a window into Mars's interior, revealing layers of rock and sediment that hold clues to the planet's geological and climatic history. Despite its arid present, Mars continues to harbor water, albeit mostly in frozen or vapor form. At its poles lie massive ice caps, composed of water ice and dry ice, frozen carbon dioxide, which expand and contract with the changing seasons. Beneath the surface, radar data from orbiting spacecraft has detected signs of liquid water trapped under layers of ice, possibly kept warm by salts and pressure. These subsurface reservoirs raise tantalizing possibilities for microbial life, shielded from the harsh conditions above. Could these hidden pockets of water host organisms adapted to survive in extreme environments? It's a question scientists are eager to explore. The search for life on Mars extends beyond its hidden waters. NASA's Perseverance rover and China's Zhurong rover are currently traversing the Martian surface, analyzing rocks and soil for biosignatures, chemical traces left behind by ancient microbes. One of their key targets is Jezero Crater, a dried-up lakebed believed to have once contained a thriving body of water. By studying the sediments deposited there billions of years ago, researchers hope to uncover organic molecules or other evidence of past life. Meanwhile, future missions aim to return samples to Earth, where advanced laboratories can conduct detailed analyses impossible to perform on site. Mars's thin atmosphere poses both challenges and opportunities for exploration. Composed primarily of carbon dioxide, it offers little protection against radiation or temperature extremes. Daytime highs near the equator can reach a balmy 70 degrees Fahrenheit or 20 degrees Celsius, while nighttime lows plummet to -100 degrees Fahrenheit or -73 degrees Celsius. Yet despite these harsh conditions, Mars remains a prime candidate for human exploration. Its gravity, about 38% of Earth's, makes it easier to land and take off compared to heavier planets like Venus. And its proximity to Earth, ranging from 34 million to 250 million miles or 55 million to 400 million kilometers, makes it the next logical step in humanity's journey into deep space. Efforts to send humans to Mars are already underway. SpaceX Starship, NASA's Artemis program, and international collaborations all envision a future where astronauts walk on Martian soil, conducting experiments and laying the groundwork for potential colonization. Such missions will require innovative solutions to overcome the planet's challenges, from producing oxygen and fuel, using local resources, to growing food in controlled environments. The technology developed for Mars could revolutionize life on Earth, driving advancements in sustainability, medicine, and engineering. But Mars isn't just a destination for science, it's also a muse for art, literature, and philosophy. For centuries, writers and dreamers have imagined it as a frontier for adventure, a refuge for humanity, or even a cradle of alien civilizations. H.G. Wells' The War of the Worlds envisioned Martians invading Earth, while Ray Bradbury's The Martian Chronicles explored themes of colonization and cultural exchange. These stories reflect our hopes, fears, and aspirations, reminding us that Mars is more than a scientific target. It's a symbol of humanity's quest for knowledge and meaning. As we continue to unlock Mars's secrets, we're reminded of how much we still don't know. Is there, or was there, life on Mars? What caused its climate to change so dramatically? Could humans one day call it home? Each discovery brings new questions, deepening our fascination with this enigmatic world. Mars challenges us to think bigger, to push boundaries, and to embrace uncertainty as an opportunity rather than an obstacle. In many ways, Mars mirrors Earth's own story, a tale of transformation, resilience, and possibility. Its dusty plains and towering peaks whisper of a time when water flowed freely, when wind sculpted dunes, and when perhaps life found a foothold. Whether or not Mars harbors answers to our deepest questions, its very existence inspires us to keep exploring, to keep dreaming, and to keep striving for a better understanding of our place in the cosmos. And so as we peer across the void at the red planet, let us remember that Mars is not just a neighbor, it's a mirror, reflecting our curiosity, our ingenuity, and our unyielding desire to reach beyond the horizon. In its silence lies a promise that no matter how far we travel, the spirit of discovery will always guide us forward. Jupiter, king of the planets. In the vast court of the solar system, one planet reigns supreme, Jupiter, the largest and most majestic of them all. With a diameter stretching nearly 87,000 miles, or 140,000 kilometers, this gas giant is so immense that it accounts for 70% of the total mass of all the planets combined. Its sheer size and commanding presence have earned it the title, King of the Planets. But Jupiter's true majesty lies not just in its bulk, but in the intricate tapestry of storms, moons, and mysteries that swirl within its domain. Jupiter's most iconic feature is undoubtedly the Great Red Spot, a colossal storm larger than Earth itself. This swirling tempest has raged for at least 350 years, possibly much longer, and shows no signs of abating anytime soon. Winds within the Great Red Spot reach speeds of up to 400 miles per hour or 650 kilometers per hour, making it one of the most violent weather systems ever observed. Yet, despite its ferocity, the storm moves with an almost hypnotic grace, a crimson whirlpool adrift in Jupiter's turbulent atmosphere. Scientists believe the Great Red Spot is fueled by heat rising from deep within the planet, a reminder of the dynamic processes shaping Jupiter's interior. But the Great Red Spot is just one chapter in Jupiter's story. The planet's atmosphere is a kaleidoscope of colors, painted in bands of white, orange, brown, and red. These stripes are caused by jet streams that race around the planet at hundreds of miles per hour, separating regions of rising and falling gases. The lighter bands, known as zones, are areas where ammonia clouds reflect sunlight, while the darker bands, called belts, reveal deeper layers of the atmosphere. Together they create a mesmerizing pattern that shifts and evolves over time, like brushstrokes on an ever-changing canvas. Beneath these swirling clouds lies a world unlike any other. Jupiter does not have a solid surface. Instead, its outer layers transition gradually from gas to liquid as pressure increases with depth. At its core, or what scientists suspect might be a core, lies a dense region of rock, metal, and perhaps even a slurry of hydrogen and helium under unimaginable pressures. Surrounding this core is a layer of metallic hydrogen, a strange state of matter formed when hydrogen is squeezed so tightly that it behaves like an electrical conductor. This metallic hydrogen generates Jupiter's powerful magnetic field, the strongest of any planet in the solar system, shielding the planet and its moons from harmful cosmic radiation. Speaking of moons, Jupiter boasts a retinue of satellites that rivals the splendor of its atmosphere. With 92 confirmed moons and counting, it has the largest family of natural satellites in the solar system. Among them are the 4 Galilean moons, named after their discoverer, Galileo Galilei, who first spotted them through his telescope in 1610. Io, Europa, Ganymede, and Callisto each offer a glimpse into the diversity of worlds that orbit Jupiter. Io is a fiery world of constant volcanic activity, its surface dotted with lava lakes and plumes of sulfur spewing miles into the sky. Tidal forces from Jupiter's immense gravity stretch and squeeze Io, generating enough heat to power its eruptions. In stark contrast, Europa is a frozen moon encased in a shell of ice, beneath which lies a global ocean that may harbor more water than all of Earth's seas combined. This hidden ocean, kept warm by tidal heating, is considered one of the most promising places in the solar system to search for extraterrestrial life. Ganymede, the largest moon in the solar system, surpasses even the planet Mercury in size. It possesses its own magnetic field, a rarity among moons, and may also contain a subsurface ocean. Callisto, meanwhile, is an ancient, heavily cratered world that serves as a time capsule of the early solar system. Each of these moons tells a unique story, offering insights into the forces that shape planetary systems. Jupiter's influence extends far beyond its immediate vicinity. Its immense gravitational pull acts as a cosmic vacuum cleaner, capturing comets and asteroids that might otherwise threaten the inner planets. One famous example occurred in 1994 when fragments of comet Shoemaker-Levy 9 collided with Jupiter, creating massive explosions visible from Earth. These impacts serve as a reminder of Jupiter's role as a guardian of the solar system, protecting smaller worlds like ours from catastrophic collisions. Yet for all its grandeur, Jupiter remains shrouded in mystery. How did it form? What lies at its core? And how does its complex interplay of storms and magnetic fields arise? Missions like NASA's Juno spacecraft are working to unravel these enigmas, peering beneath Jupiter's thick cloud layers and mapping its magnetic field with unprecedented precision. Juno's findings have already challenged long-held assumptions, revealing that Jupiter's core may be fuzzy and diffuse rather than compact, and that its auroras behave differently than those on Earth. Jupiter's allure lies not only in its scientific significance, but also in its symbolic power. Throughout history, it has been associated with gods and rulers, from the Roman deity Jupiter to the Babylonian Marduk. Its prominence in the night sky made it a beacon of authority and strength, qualities reflected in its modern nickname, King of the Planets. Even today, Jupiter inspires awe, a celestial monarch whose reign stretches across the heavens. As we gaze upon Jupiter, we're reminded of the boundless complexity of the universe. Its storms rage, its moons dance, and its magnetic embrace shields countless worlds from harm. It is a planet of extremes, a place where beauty and chaos coexist in perfect harmony. Whether viewed through a telescope or explored by robotic probes, Jupiter invites us to dream bigger, to ask harder questions, and to marvel at the wonders of creation. And so, as we continue our journey through the solar system, let us pause to honor Jupiter, not just as a king among planets, but as a testament to the enduring mysteries of the cosmos. In its swirling clouds and distant moons, we find echoes of our own curiosity, a reminder that the quest for knowledge knows no bounds. Jupiter beckons us onward, a guiding light in humanity's eternal pursuit of understanding. Saturn, the ringed wonder. Few sights in the cosmos capture the imagination quite like Saturn, the solar system's crown jewel. With its dazzling rings encircling a golden globe, Saturn is often described as the most beautiful planet, a celestial masterpiece that seems almost too perfect to be real. But beyond its breathtaking appearance lies a world of complexity and intrigue, where icy particles dance in orbit, storms churn beneath clouds, and moons tell stories older than time itself. Saturn is not just a visual wonder, it's a testament to the elegance and mystery of the universe. The first thing anyone notices about Saturn is its rings, a sprawling system of icy debris stretching thousands of miles above the planet's equator. These rings are made up of countless particles ranging in size from tiny grains of sand to massive chunks as large as mountains. Despite their grandeur, the rings are remarkably thin, averaging only about 30 feet or 10 meters in thickness. From afar, they appear solid, but up close, they reveal themselves as a dynamic tapestry of motion, with individual particles orbiting Saturn at speeds determined by their distance from the planet. Scientists believe the rings formed relatively recently, perhaps within the last few 100 million years, when a moon or comet came too close to Saturn and was torn apart by its immense gravity. Saturn's rings are divided into distinct sections, labeled alphabetically based on the order of their discovery. The brightest and most prominent are the A, B, and C rings, separated by gaps such as the Cassini division, a dark band visible even through small telescopes. Within these rings, intricate structures emerge, including spiral waves, spokes, and clumps of material shaped by gravitational interactions with Saturn's moons. One particularly fascinating feature is the F ring, a narrow, twisted ribbon kept in place by two tiny shepherd moons, Prometheus and Pandora, whose gravitational tugs sculpt its edges. The interplay between Saturn's rings and its moons creates a cosmic ballet, a delicate balance of forces that has fascinated astronomers for centuries. But Saturn's allure extends far beyond its rings. Beneath its hazy atmosphere lies a planet unlike any other. Saturn is a gas giant, composed primarily of hydrogen and helium, similar to Jupiter, but its lower density makes it unique. It's the only planet in the solar system that could float in water if there were a bathtub large enough to hold it. Its average density is less than that of liquid water, a quirk of its composition and structure that underscores its ethereal nature. Yet despite its lightweight build, Saturn exerts an extraordinary gravitational pull, shaping the orbits of its many moons and influencing the dynamics of the entire Saturnian system. Saturn's atmosphere is a swirling sea of clouds, painted in shades of gold, beige, and caramel. Unlike Jupiter's bold stripes, Saturn's bands are subtler, blending seamlessly into one another. High-speed winds whip around the planet, reaching speeds of over 1,100 miles per hour or 1,800 kilometers per hour, near the equator, the fastest in the solar system. These winds fuel massive storms, including a hexagonal-shaped jet stream at Saturn's North Pole. This six-sided vortex, larger than Earth, rotates steadily, its geometric precision defying easy explanation. It's a reminder that even in the chaos of Saturn's weather, patterns of order can emerge. Saturn's family of moons adds another layer of wonder to this already extraordinary planet. With 146 confirmed moons, and likely more waiting to be discovered, Saturn boasts one of the most diverse collections of satellites in the solar system. Among them, Titan stands out as a world unto itself. Larger than Mercury, Titan is the second largest moon in the solar system and the only one with a thick atmosphere. Composed mostly of nitrogen, its air is eerily similar to Earth's early atmosphere, and its surface is dotted with lakes and rivers, but instead of water, these bodies are filled with liquid methane and ethane. Titan's frigid temperatures make it a chemist's playground, offering clues about prebiotic chemistry and the potential for life in environments vastly different from our own. Another remarkable moon is Enceladus, a small, icy world that punches far above its weight in terms of scientific importance. Beneath its frozen crust lies a global ocean of salty water, kept warm by tidal forces from Saturn. Geysers erupting from cracks near Enceladus' south pole spew plumes of water vapor and organic molecules into space, providing direct access to material from its subsurface ocean. These plumes have made Enceladus a prime target in the search for extraterrestrial life, as they offer a rare opportunity to sample the contents of an alien sea without drilling through miles of ice. Other moons, like Mimas, Iapetus, and Hyperion, each contribute their own peculiarities to Saturn's story. Mimas, with its enormous Herschel crater, looks eerily like the Death Star from Star Wars. Iapetus features a striking two-tone coloration, half bright white and half dark charcoal, thought to result from dust accumulation on one side. Hyperion, meanwhile, resembles a porous sponge, its irregular shape and chaotic rotation hinting at a violent past. Together, these moons paint a picture of a planetary system shaped by collisions, migrations, and the relentless pull of Saturn's gravity. Exploring Saturn has been a monumental challenge, but humanity has risen to the occasion. NASA's Cassini spacecraft spent over a decade studying the planet and its moons, revealing secrets hidden beneath its clouds and rings. Cassini's daring maneuvers included flying through Enceladus's plumes and skimming the outer edges of Saturn's rings, capturing data that transformed our understanding of the Saturnian system. In its final act, Cassini plunged into Saturn's atmosphere, burning up in a fiery farewell that ensured it wouldn't contaminate any potentially habitable moons. Its legacy lives on in the wealth of knowledge it provided, inspiring future missions to delve deeper into Saturn's mysteries. Saturn's beauty is matched only by its scientific significance. It serves as a natural laboratory for studying processes that occur throughout the universe, from the formation of planets and moons to the behavior of magnetic fields and atmospheres. Its rings, though temporary on cosmic timescales, offer insights into how planetary systems evolve, and its moons, especially Titan and Enceladus, hold the promise of answering fundamental questions about the origins of life and the conditions necessary for its survival. As we gaze upon Saturn, we're reminded of the delicate balance that defines existence in the cosmos. Its rings shimmer like jewels, yet they are fleeting, destined to dissipate over millions of years. Its storms rage, yet they follow patterns dictated by physics and mathematics. Its moons orbit in harmony, yet their surfaces bear the scars of ancient upheavals. Saturn embodies both permanence and impermanence, a paradox that mirrors the human experience itself. And so, as we turn our eyes skyward to admire this ringed wonder, let us carry with us a sense of gratitude for the chance to witness such splendor, for the curiosity that drives us to explore, and for the lessons Saturn teaches us about the interconnectedness of all things. Whether viewed through a telescope or studied by robotic explorers, Saturn reminds us that beauty and knowledge go hand in hand, each enriching the other in ways we're only beginning to understand. It is a beacon of inspiration, a symbol of the infinite possibilities that await us in the vastness of space. Uranus, the sideways ice giant. In the distant reaches of the solar system, where sunlight dims to a faint glow, lies a planet that defies convention, Uranus, the enigmatic ice giant, with a penchant for spinning on its side. Unlike any other planet, Uranus orbits the Sun tipped over at an extreme angle, its poles taking turns basking in sunlight while the rest of the planet plunges into decades-long shadows. This peculiar tilt, combined with its icy composition and mysterious blue-green hue, makes Uranus one of the most intriguing worlds in the solar system, a cosmic oddity that challenges our understanding of planetary formation and behavior. At first glance, Uranus appears serene, a pale turquoise orb floating silently against the blackness of space. Its color comes from methane in its atmosphere, which absorbs red light and reflects blue, giving the planet its distinctive appearance. But beneath this calm exterior lies a world of complexity. Uranus is classified as an ice giant, not because it's covered in ice, but because its interior is composed largely of ice, compounds like water, ammonia, and methane, mixed with rock and metal. These materials exist under crushing pressures and temperatures so low they're almost unimaginable, creating a slushy, dense layer beneath the planet's gaseous envelope. What truly sets Uranus apart, however, is its bizarre orientation. Most planets spin upright relative to their orbital plane, with slight tilts that give rise to seasons. Earth, for example, has an axial tilt of about 23 degrees, resulting in our familiar four-season cycle. Uranus, by contrast, is tilted at a staggering 98 degrees, essentially rolling along its orbit like a ball rather than spinning like a top. This extreme tilt means that during Uranus's 84-year journey around the Sun, each pole experiences 42 years of continuous daylight, followed by 42 years of darkness. The result is a seasonal pattern unlike anything else in the solar system, with dramatic shifts in weather and atmospheric dynamics. The reasons behind Uranus's unusual tilt remain a subject of debate among scientists. One leading theory suggests that early in its history, Uranus may have been struck by a massive object, perhaps a protoplanet or even a series of collisions, that knocked it onto its side. Another possibility is that gravitational interactions with neighboring planets during the solar system's chaotic infancy played a role. Whatever the cause, this sideways spin has profound implications for the planet's climate and internal structure, making Uranus a natural laboratory for studying how extreme conditions shape planetary evolution. Beneath its thick atmosphere, Uranus harbors surprises that stretch the limits of our imagination. Hidden deep within the planet lies a subsurface ocean of superheated water and ammonia. This layer, often referred to as an ocean mantle, exists in a strange state between liquid and solid due to the immense pressure. Some researchers speculate that this ocean could harbor unique forms of chemistry, potentially offering insights into the origins of life in environments far removed from traditional habitability. Turning to its atmosphere, Uranus reveals subtleties that reward closer inspection. Though it lacks the dramatic storms and colorful bands seen on Jupiter and Saturn, it hosts subtle weather patterns driven by its unusual tilt. During equinoxes, when the sun shines directly over Uranus's equator, faint cloud formations appear, likely caused by rising currents of warmer gas. These clouds are composed of methane ice crystals, giving them a bright, reflective quality. In contrast, during solstices, when one hemisphere faces the sun continuously, the atmosphere grows calmer, with fewer visible features. Despite these variations, Uranus remains relatively quiet compared to its gas giant cousins, earning it a reputation as the bland planet, though closer inspection reveals a subtler kind of beauty. Surrounding Uranus is a family of moons, each with its own story to tell. With 27 known satellites, Uranus's moons fall into two categories: the larger, irregularly shaped ones that likely formed from leftover debris after the planet's creation, and the smaller, more distant moons that may have been captured asteroids. Among the largest is Titania, named after a character from Shakespeare's A Midsummer Night's Dream. At just under 1,000 miles or 1,600 kilometers in diameter, Titania is pockmarked with craters and intersected by deep canyons, evidence of ancient geological activity. Oberon, another major moon, shares similar features, including a dark reddish patch thought to be material ejected from impacts. Perhaps the most captivating of Uranus's moons is Miranda, a small, oddly shaped satellite that looks like it was pieced together from mismatched fragments. Its surface is a jumble of ridges, valleys, and fault lines, suggesting a violent past marked by tectonic upheavals. Some scientists believe Miranda may have been shattered by collisions and then reassembled, leaving behind its patchwork appearance. Others propose that tidal forces from Uranus caused partial melting within Miranda, leading to resurfacing events that erased older terrain. Whatever the explanation, Miranda stands as a testament to the dynamic processes shaping even the smallest worlds. Despite its allure, Uranus remains one of the least explored planets in the solar system. To date, only one spacecraft, NASA's Voyager 2, has visited the planet, flying by in 1986. During its brief encounter, Voyager 2 revealed Uranus's rings, a faint, dusty system of 13 known bands, and provided the first close-up images of its moons. Since then, much of what we know about Uranus comes from ground-based telescopes and the Hubble Space Telescope, which continue to monitor changes in its atmosphere and ring system. Future missions, including potential orbiters and landers, could unlock new secrets, shedding light on everything from its magnetic field to the nature of its interior. One of Uranus's most puzzling traits is its magnetic field, which is tilted nearly 60 degrees relative to its rotational axis and offset from the planet's center. This lopsided magnetosphere creates wildly fluctuating auroras near Uranus's poles, unlike the stable displays seen on Earth. Scientists believe this asymmetry arises from the planet's unusual internal structure, particularly the presence of electrically conductive fluids deep within its icy mantle. Understanding Uranus's magnetic field could provide valuable insights into how such fields form and evolve across different types of planets. Peering deeper into Uranus's mysteries reminds us of the boundless curiosity that drives scientific exploration. This distant, sideways world challenges us to think beyond the familiar, to embrace the unknown, and to seek answers to questions we've yet to fully articulate. Uranus teaches us that even in the coldest, darkest corners of the solar system, there is wonder waiting to be discovered. Consider Uranus not just as a distant planet, but as a symbol of humanity's enduring quest for knowledge. Its sideways spin and icy depths invite us to expand our horizons and deepen our understanding of the cosmos. Whether through telescopes or future spacecraft, Uranus will continue to inspire curiosity, urging us to explore the edges of our solar system and beyond. Dwarf planets, tiny worlds. In the vast expanse of the solar system, not all celestial bodies fit neatly into the category of planet. Some are smaller, quieter, and often overlooked, yet they hold their own unique charm and significance. These are the dwarf planets, tiny worlds that defy easy classification, but offer a wealth of insights into the formation and evolution of our cosmic neighborhood. From the icy plains of Pluto to the distant reaches of Eris, these diminutive objects remind us that size is no measure of importance. The most famous of the dwarf planets is Pluto, a world that captured the hearts of millions long before its reclassification in 2006. Once considered the ninth planet, Pluto was demoted to dwarf planet status after the International Astronomical Union defined a planet as an object that orbits the Sun, is spherical due to its own gravity, and has cleared its orbit of other debris. Pluto fails the third criterion, sharing its orbital zone with countless other objects in the Kuiper Belt, a region of icy remnants from the early solar system. Yet far from diminishing its appeal, this reclassification has only deepened our fascination with Pluto and its fellow dwarf planets. Pluto's surface is a patchwork of terrains, each telling a story of ancient processes and ongoing change. The heart-shaped feature known as Toumbaugh Regio, named after Pluto's discoverer Clyde Toumbaugh, dominates its appearance. This vast plain of frozen nitrogen, carbon monoxide, and methane stretches for hundreds of miles and shows signs of recent geological activity. Nearby, jagged mountains of water ice rise like shards against the smooth plains, their towering peaks reaching heights comparable to Earth's Rocky Mountains. These features suggest that despite its small size and frigid temperatures, Pluto remains geologically active, driven by internal heat and complex interactions between its surface and subsurface layers. Beyond Pluto lies a host of other dwarf planets, each with its own distinct personality. Eris, discovered in 2005, is one of the largest and most distant dwarf planets, residing in the scattered disk, a region even farther out than the Kuiper Belt. With a diameter slightly smaller than Pluto's, Eris sparked the debate that led to the redefinition of planet. Its highly elliptical orbit takes it 3 times farther from the Sun than Pluto, at its farthest point, plunging it into an icy darkness where sunlight is little more than a faint glimmer. Despite its remoteness, Eris boasts a bright, reflective surface, likely covered in frost that forms when methane freezes out of its thin atmosphere during its centuries-long winter. Another intriguing dwarf planet is Haumea, shaped like an elongated rugby ball due to its rapid rotation, spinning on its axis once every 4 hours. Haumea is one of the fastest rotating large objects in the solar system. This dizzying spin has flattened its poles and stretched its equator, creating a distinctly oblong shape. Haumea's surface is covered in crystalline water ice, a material that shouldn't exist in such pristine form, given the harsh conditions of space. Scientists speculate that recent impacts may have exposed fresh ice, offering clues about the dynamic nature of this distant world. Makemake, named after a Polynesian creator god, is another Kuiper Belt resident that stands out for its reddish hue. This coloration comes from complex organic molecules called tholins, which form when ultraviolet light interacts with methane and nitrogen on its surface. Unlike Pluto, Makemake lacks a significant atmosphere, leaving its icy terrain exposed to the vacuum of space. Despite its isolation, Makemake harbors a moon named S2015-136472-1, affectionately nicknamed MK2, which provides valuable information about the dwarf planet's mass and composition. Closer to home, Ceres resides in the asteroid belt between Mars and Jupiter, making it the only dwarf planet located within the inner solar system. With a diameter of about 590 miles or 940 kilometers, Ceres is both the smallest and the closest dwarf planet to Earth. Its surface is a mix of rock and ice, dotted with craters and mysterious bright spots believed to be deposits of salt left behind by evaporating briny water. NASA's Dawn mission revealed evidence of a subsurface ocean beneath Ceres's crust, raising tantalizing questions about the potential for habitability in unexpected places. What makes dwarf planets so compelling is their diversity. They represent a bridge between the rocky planets of the inner solar system and the icy bodies of the outer regions. Their compositions, orbits, and histories provide critical clues about how the solar system formed and evolved over billions of years. For example, the Kuiper Belt objects, including Pluto, Eris, and others, are thought to be remnants from the primordial disk of gas and dust that gave rise to the planets. By studying these tiny worlds, scientists can piece together the puzzle of our solar system's chaotic infancy. Exploring dwarf planets poses unique challenges due to their distance and small size. New Horizons' flyby of Pluto in 2015 marked a historic milestone, providing humanity's first close-up look at this distant world. Images and data from the mission revealed a surprisingly complex and dynamic environment, challenging preconceived notions about what such a remote and cold place could be like. Future missions to other dwarf planets, though technically demanding, promise to unlock even more secrets, helping us understand not just our own solar system, but also the broader context of planetary systems throughout the galaxy. Dwarf planets also invite philosophical reflection. Their existence blurs the line between categories, forcing us to reconsider how we define and classify objects in the cosmos. Are they failed planets? Or are they something entirely different? Perhaps they represent a new class of celestial bodies that challenge traditional hierarchies and expand our understanding of what it means to be a world. In embracing their ambiguity, we embrace the complexity and richness of the universe itself. These tiny worlds may lack the grandeur of their larger planetary siblings, but they possess a quiet dignity all their own. Each dwarf planet is a testament to the forces that shape the solar system, a fragment of history preserved in ice and stone. They remind us that exploration is not just about seeking the biggest or brightest, it's about uncovering the stories hidden in the smallest details. When we think of dwarf planets, let us celebrate their individuality, their quirks, their mysteries, and their resilience. They are proof that even in the vastness of space, there is room for the small and the overlooked to shine. Whether through telescopes or spacecraft, these tiny worlds beckon us to keep looking, keep learning, and keep marveling at the wonders of the cosmos. Moons, cosmic companions. In the grand theater of the solar system, planets often take center stage, but their loyal companions, the moons, deserve equal admiration. These celestial sidekicks orbit their parent planets with quiet dedication, each one a world unto itself, shaped by unique histories and forces. From Earth's own moon to the icy giant's distant satellites, moons are cosmic storytellers, revealing clues about the formation of planets, the dynamics of gravity, and even the potential for life beyond our home. Earth's moon is perhaps the most familiar of these companions, a steadfast presence in our night sky that has inspired myths, guided explorers, and influenced the tides for billions of years. With a diameter of about 2,160 miles or 3,475 kilometers, it's the fifth largest moon in the solar system, yet its proximity makes it appear larger than any other. The moon's surface is a patchwork of dark plains called Maria, formed by ancient volcanic eruptions, and bright highlands scarred by countless craters left behind by asteroid impacts. These features tell the story of a violent past when the young solar system was still cluttered with debris. The moon's influence on Earth cannot be overstated. Its gravitational pull creates the tides, shaping coastlines and ecosystems around the globe. Without the moon, Earth's axial tilt would wobble unpredictably, leading to extreme climate swings that could make life as we know it impossible. Scientists believe the moon formed nearly 4.5 billion years ago when a Mars-sized object collided with Earth, ejecting molten debris into orbit. Over time, this material coalesced into the moon we see today, a reminder of the cataclysmic events that shaped our planet. But Earth's moon is just one chapter in the rich anthology of lunar worlds scattered across the solar system. Jupiter alone boasts dozens of moons, each with its own personality. Ganymede, the largest moon in the solar system, surpasses even the planet Mercury in size. Beneath its icy crust lies a subsurface ocean that may hold more water than all of Earth's seas combined. Europa, another Jovian moon, captivates scientists with its smooth, cracked surface, hinting at a global ocean beneath. This hidden sea, warmed by tidal forces from Jupiter, is considered one of the best places to search for extraterrestrial life. Could hydrothermal vents on Europa's ocean floor harbor microbial organisms? It's a tantalizing possibility that future missions hope to explore. Saturn's moons add further intrigue to the tapestry of lunar diversity. Titan, Saturn's largest moon, stands apart as the only satellite with a thick atmosphere, composed primarily of nitrogen like Earth's. Its surface is dotted with lakes and rivers, but instead of water, they're filled with liquid methane and ethane. Titan's frigid temperatures make it an alien world unlike any other, offering insights into prebiotic chemistry and the conditions necessary for life. Enceladus, meanwhile, is a small, icy moon that punches far above its weight in scientific importance. Geysers erupting from its south pole spew plumes of water vapor and organic molecules into space, providing direct access to material from its subsurface ocean. These discoveries have made Enceladus a prime target in the search for habitable environments. Mars offers a stark contrast with its two diminutive moons, Phobos and Deimos. These irregularly shaped satellites resemble potatoes more than traditional moons, likely captured asteroids pulled into Mars's orbit long ago. Phobos, the larger of the two, is slowly spiraling inward toward Mars, destined to either crash into the planet or break apart to form a ring system in tens of millions of years. Deimos, farther out, drifts away ever so slightly, eventually escaping Mars's gravitational grasp. Together, they serve as reminders of the dynamic processes that govern planetary systems. Even the distant ice giants Neptune and Uranus host fascinating moons. Triton. Neptune's largest moon orbits backward relative to the planet's rotation, suggesting it was once a free-floating object captured by Neptune's gravity. Its surface features geysers of nitrogen gas and vast plains of frozen nitrogen, evidence of ongoing geological activity. Miranda, a moon of Uranus, looks like a jigsaw puzzle of terrains, with ridges, valleys, and fault lines, hinting at a turbulent past. These moons remind us that even in the coldest, darkest corners of the solar system, there is beauty and complexity waiting to be uncovered. Moons also play a critical role in stabilizing their parent planets. For example, Charon, Pluto's largest moon, is so massive relative to Pluto that the two bodies orbit a common center of gravity located outside Pluto itself. This unique relationship classifies them as a binary system, challenging traditional notions of what constitutes a moon. Similarly, Saturn's shepherd moons, such as Prometheus and Pandora, sculpt the edges of its rings, maintaining their delicate structure through gravitational interactions. Exploring moons has yielded some of humanity's most profound discoveries. NASA's Apollo missions brought back samples from the moon, revolutionizing our understanding of its composition and origin. Voyager and Cassini spacecraft revealed the wonders of Jupiter's and Saturn's moons, while New Horizons provided stunning images of Pluto's moon Charon. Future missions, including plans to return humans to the moon under NASA's Artemis program and robotic landers destined for Europa and Titan, promise to deepen our knowledge of these enigmatic worlds. What makes moons so captivating is their sheer variety. They range from barren rocks to potential havens for life, from tiny specks to giants rivaling planets. Their surfaces bear witness to the forces that shape the cosmos: impacts, volcanism, tides, and erosion, offering a window into the past and present of the solar system. By studying moons, we gain insights not only into the history of individual planets, but also into the broader mechanisms that govern planetary systems. These cosmic companions remind us that even the smallest objects can have outsized significance. They challenge us to think beyond categories, to embrace complexity, and to marvel at the interconnectedness of the universe. Whether viewed through a telescope or explored by spacecraft, moons inspire wonder and curiosity, urging us to keep asking questions and seeking answers. As we look to the skies and ponder the mysteries of the cosmos, let us not overlook these silent sentinels. Moons are more than mere satellites. They are storytellers, guardians, and laboratories. Each one carries the echoes of creation, the scars of collisions, and the promise of discovery. In their quiet orbits, they remind us that even in the vastness of space, there is room for connection, for Earth's cosmic companions are part of our shared journey through the stars. Asteroids, space's rocky remnants. Scattered throughout the solar system like ancient breadcrumbs, asteroids are the leftover building blocks of planets, remnants from a time when the cosmos was still piecing itself together. These rocky fragments may lack the grandeur of planets or the mystique of comets, but they hold invaluable clues about the solar system's formation and evolution. From their chaotic orbits to their potential to reshape life on Earth, asteroids remind us that even the smallest objects can have monumental significance. The majority of asteroids reside in the asteroid belt, a vast region between Mars and Jupiter, where millions of these rocky bodies drift silently through space. Stretching over 100 million miles, or 160 million kilometers, the asteroid belt is home to everything from tiny pebbles to massive boulders hundreds of miles across. Despite its immense size, the belt is surprisingly sparse. Spacecraft traveling through it rarely encounter obstacles, as the distances between individual asteroids are vast. The largest resident of this region is Ceres, which spans about 590 miles, or 940 kilometers in diameter. Once classified as an asteroid, Ceres is now recognized as a dwarf planet, bridging the gap between these two categories of celestial objects. Asteroids come in a variety of shapes, sizes, and compositions, reflecting the diverse materials that existed in the early solar system. Some are made primarily of rock, while others consist of metal, ice, or a mix of all three. Scientists classify them into three main types based on their composition: carbonaceous, C-type, silicate, S-type, and metallic, M-type. C-type asteroids, rich in carbon compounds, are among the most common and are believed to contain organic molecules that could have contributed to the origins of life on Earth. S-type asteroids, found closer to the Sun, are composed mainly of silicate rocks and metals, while M-type asteroids are thought to be fragments of the metallic cores of long-destroyed protoplanets. One of the most famous asteroids is Vesta, a massive, irregularly shaped body located in the inner asteroid belt. With a diameter of about 326 miles or 525 kilometers, Vesta is so large that it once had volcanic activity, leaving behind basaltic plains visible on its surface today. NASA's Dawn mission revealed that Vesta bears many similarities to terrestrial planets, including evidence of past lava flows and a layered internal structure. Its surface is pockmarked with craters, the largest of which, called Resilvia, spans nearly the entire width of the asteroid. This colossal impact likely sent debris hurtling into space, some of which eventually reached Earth as meteorites. But asteroids are not confined to the asteroid belt. Near-Earth asteroids, or NEAs, orbit closer to our planet, posing both opportunities and risks. These wandering rocks occasionally pass within millions of miles of Earth, making them accessible targets for exploration and resource extraction. Companies and space agencies have begun eyeing asteroids as potential sources of valuable minerals, such as platinum and rare earth elements, which could fuel future industries in space. However, NEAs also pose a threat. While most burn up harmlessly in Earth's atmosphere, larger ones can cause catastrophic damage if they collide with our planet. The infamous Chicxulub impactor, which struck Earth 66 million years ago, triggered the mass extinction of the dinosaurs and reshaped the course of life on our planet. Understanding asteroids' behavior is crucial for predicting and mitigating potential impacts. NASA's OSIRIS-REx mission recently visited Bennu, a near-Earth asteroid roughly the size of the Empire State Building. By collecting samples from Bennu's surface and returning them to Earth, scientists hope to learn more about its composition and history. Surprisingly, Bennu turned out to be far rougher and rockier than expected, challenging assumptions about how these small bodies evolve over time. Additionally, data from the mission revealed that Bennu has a slight chance of impacting Earth in the late 22nd century, a reminder of why studying these objects is so important. Asteroids also serve as time capsules, preserving materials unchanged since the solar system's infancy. Their chemical makeup provides insights into the conditions that existed billions of years ago, before planets formed. For example, Ryugu, another near-Earth asteroid explored by Japan's Hayabusa 2 mission, appears to be rich in hydrated minerals and organic compounds. Samples returned from Ryugu offer a glimpse into the raw ingredients that might have seeded Earth with water and the precursors to life. Such discoveries underscore the importance of asteroids not just as relics of the past, but as keys to understanding the origins of life itself. Despite their scientific value, asteroids remain enigmatic and unpredictable. Their orbits can shift due to gravitational interactions with planets, particularly Jupiter, whose immense gravity acts as a cosmic shepherd. Occasionally, these perturbations send asteroids careening into new trajectories, sometimes bringing them dangerously close to Earth. Other times, they're flung outward into the Kuiper belt or even ejected from the solar system entirely. This dynamic dance highlights the delicate balance that governs the movement of objects in space. Exploring asteroids has become a priority for space agencies worldwide. Missions like OSIRIS-REx and Hayabusa 2 represent humanity's first steps toward harnessing the resources of these ancient worlds. In addition to advancing science, asteroid mining could provide the raw materials needed to sustain human presence in space, reducing the need to launch heavy payloads from Earth. Imagine refueling spacecraft or constructing habitats using metals extracted directly from asteroids, a vision that seems straight out of science fiction but may soon become reality. Yet asteroids remind us of our vulnerability as well as our ingenuity. They are reminders that the solar system is a dynamic and sometimes hazardous place. Efforts to detect and track potentially hazardous asteroids are ongoing, with organizations like NASA's Planetary Defense Coordination Office working tirelessly to identify threats and develop strategies to deflect incoming objects. Technologies such as kinetic impactors and gravity tractors are being tested to ensure we're prepared should an asteroid ever threaten Earth again. These rocky remnants may seem insignificant compared to the majesty of planets or the brilliance of stars, but they carry profound meaning. They connect us to the dawn of the solar system, offering glimpses into the processes that shaped our cosmic neighborhood. They challenge us to innovate, inspiring technologies that could safeguard our planet and expand our reach into the universe. And they remind us of the fragility of life, urging us to cherish and protect the pale blue dot we call home. When we think of asteroids, let us see them not merely as chunks of rock, but as storytellers, messengers, and teachers. Each one carries the echoes of creation, the scars of collisions, and the promise of discovery. Whether viewed through telescopes, studied via robotic probes, or mined for resources, asteroids continue to captivate and inspire, reminding us that even in the vastness of space, there is room for connection, for these rocky remnants are part of our shared journey through the stars. Meteors, shooting stars explained. Few sights in the night sky are as magical as a streak of light flashing across the heavens, a fleeting moment of beauty that has inspired wonder and awe for millennia. These dazzling displays, often called shooting stars, are not stars at all but meteors, fragments of rock and metal from space, burning up as they enter Earth's atmosphere. Though brief and ephemeral, these fiery visitors carry stories of cosmic origins, ancient collisions, and the dynamic forces that shape our solar system. Meteors begin their journey far beyond Earth, originating from comets, asteroids, or even the debris left behind by planetary formation. When comets pass close to the Sun, their icy surfaces vaporize, releasing dust and small particles that trail along their orbital paths. Similarly, collisions between asteroids can scatter fragments into space, creating streams of debris that intersect Earth's orbit. When our planet plows through these streams, the particles, ranging in size from grains of sand to boulders, are pulled toward Earth by gravity, igniting a spectacle in the sky. Meteoroid is the term for a space rock before it enters Earth's atmosphere. The moment a meteoroid meets the atmosphere, its fate is sealed. Traveling at speeds of up to 160,000 miles per hour, or 257,000 kilometers per hour, these objects slam into the air with incredible force. The intense friction generates heat, causing the surrounding air to glow and the meteoroid itself to burn up in a blaze of light. This process, known as ablation, transforms the object into a meteor, a bright streak visible for just a few seconds. Most meteors disintegrate completely before reaching the ground, their energy dissipating harmlessly in the upper atmosphere. Despite their brevity, meteors leave lasting impressions. Ancient cultures interpreted them as omens, messages from the gods, or signs of impending change. Some believed they were souls ascending to the heavens, while others saw them as warnings of disaster. Today we understand meteors as natural phenomena, yet their beauty continues to captivate us. Meteor showers, which occur when Earth passes through dense streams of debris, offer some of the most reliable opportunities to witness these celestial fireworks. The Perseids, Leonids, and Geminids are among the most famous, each named after the constellation from which the meteors appear to radiate. Meteor showers are tied to specific parent bodies. For example, the Perseids originate from comet Swift-Tuttle, while the Geminids are linked to an unusual object called 3200 Phaethon, thought to be a defunct comet or asteroid. These events occur annually, as Earth crosses the orbital path of these objects, sweeping up their debris. During peak activity, observers under dark skies can see dozens or even hundreds of meteors per hour, painting the night with streaks of silver and gold. Such displays remind us of the interconnectedness of the solar system, where the remnants of distant worlds fall gently onto our own. Not all meteors vanish without a trace. Larger objects capable of surviving their fiery descent reach the ground as meteorites. These extraterrestrial rocks provide scientists with invaluable insights into the composition of the solar system. Many meteorites contain minerals and isotopes that predate the formation of planets, offering direct evidence of the conditions present during the solar system's infancy. Others, like those classified as carbonaceous chondrites, carry organic compounds and water-bearing minerals, suggesting they may have played a role in delivering the building blocks of life to early Earth. One of the most famous meteorite impacts occurred in 1908 over Tunguska, Siberia. A massive explosion flattened thousands of square miles of forest, yet no crater was found, leading scientists to conclude that the object exploded mid-air. Estimates suggest the Tunguska event released energy equivalent to 185 Hiroshima bombs, a sobering reminder of the destructive potential of even relatively small meteors. More recently, in 2013, a meteor exploded over Chelyabinsk, Russia, injuring over 1,000 people and damaging buildings with its shockwave. These incidents highlight the importance of tracking near-Earth objects and developing strategies to mitigate potential threats. While meteors pose risks, they also hold promise. Scientists study them to better understand the origins of the solar system and the processes that govern its evolution. Spectroscopic analysis of meteors' glowing trails reveals information about their chemical makeup, helping researchers identify their sources and classify them based on composition. Additionally, meteorites recovered from Earth's surface serve as natural laboratories, allowing us to examine materials that formed billions of years ago. Capturing meteors is no easy feat, given their unpredictable nature and fleeting existence. Networks of cameras and sensors around the world monitor the skies, recording fireballs and calculating their trajectories. These efforts help track the orbits of incoming objects and recover meteorites for analysis. Citizen science projects, such as the Global Fireball Observatory, enlist amateur astronomers to contribute data, expanding our ability to study these transient phenomena. Meteors also play a role in shaping Earth's environment. Tiny particles, too small to produce visible meteors, drift gently to the surface as micrometeorites, contributing a steady influx of extraterrestrial material. Over millions of years, this cosmic dust adds up, influencing everything from ocean chemistry to atmospheric composition. In a way, meteors are part of the fabric of our planet, weaving together threads from across the solar system. For all their scientific significance, meteors remain deeply personal experiences. There's something profoundly humbling about standing beneath a starry sky, watching a streak of light flash across the darkness. It's a reminder of the vastness of the universe and our place within it. Whether sparked by curiosity, reverence, or simple joy, the sight of a meteor connects us to something greater than ourselves, a shared heritage written in the language of light and motion. When we think of meteors, let us celebrate their duality, their power to both destroy and enlighten, to terrify and inspire. They are messengers from the depths of space, carrying fragments of worlds long gone and whispers of creation itself. Each streak of light is a story, a momentary glimpse into the forces that govern the cosmos, and though they vanish in an instant, their impact lingers, reminding us to look up, to wonder, and to seek answers in the infinite expanse above. Nebulae, star-birthing clouds. In the vast and silent reaches of space, where darkness seems infinite, there exist breathtaking clouds of gas and dust that glow with ethereal light. Nebulae, the celestial nurseries where stars are born. These luminous formations are among the most captivating sights in the universe, their vibrant colors and intricate shapes painting a cosmic canvas that has inspired artists, poets, and scientists alike. Nebulae are not just beautiful, they are the crucibles of creation, the places where the raw materials of the universe come together to ignite the fires of new stars. Nebulae form from the remnants of dying stars, or the diffuse matter left over from the early universe. When massive stars explode as supernovae, they scatter heavy elements like iron, carbon, and oxygen into space. These elements mix with hydrogen and helium, the building blocks of stars, to create vast clouds of interstellar material. Over time, gravity begins to pull these particles together, forming dense regions within the nebula known as protostars. As these clumps grow larger, their cores heat up under the pressure of collapsing gas, eventually reaching temperatures high enough to trigger nuclear fusion. A star is born. One of the most iconic nebula is the Orion Nebula, located in the constellation Orion and visible to the naked eye as a fuzzy patch in the night sky. This stellar nursery spans about 24 light-years, or 140 trillion miles, and contains thousands of young stars in various stages of formation. The Hubble Space Telescope has captured stunning images of this region, revealing glowing clouds of ionized gas, dark lanes of dust, and jets of material streaming away from newborn stars. The Orion Nebula is so close, at a distance of roughly 1,350 light-years, that it serves as a laboratory for studying how stars and planetary systems form. Not all nebulae are birthplaces of stars. Some mark the end of a star's life. Planetary nebulae, despite their misleading name, have nothing to do with planets. Instead, they are created when aging stars shed their outer layers, leaving behind a hot core known as a white dwarf. The ejected material expands outward, forming intricate patterns illuminated by the fading light of the central star. One of the most famous examples is the Ring Nebula, which resembles a glowing donut in space. Its delicate structure hints at the complex interactions between stellar winds and radiation that shape these dying stars' final acts. Supernova remnants are another type of nebula, born from the explosive deaths of massive stars. The Crab Nebula, located in the constellation Taurus, is perhaps the best-known example. It formed nearly 1,000 years ago when a star exploded in a supernova, visible even to ancient astronomers on Earth. Today, the Crab Nebula is a chaotic swirl of filaments and shock waves, powered by a rapidly spinning neutron star at its center called a pulsar. These remnants enrich the surrounding space with heavy elements, seeding the next generation of stars and planets. Emission nebulae, reflection nebulae, and dark nebulae each tell a different story through their unique appearances. Emission nebulae, like the Lagoon Nebulae, glow brightly because ultraviolet radiation from nearby stars excites hydrogen atoms, causing them to emit red light. Reflection nebulae, such as the Pleiades cluster surrounding haze, shine blue due to starlight scattering off tiny dust particles. Dark nebulae, on the other hand, appear as shadowy patches against brighter backgrounds, blocking light rather than emitting or reflecting it. The Horsehead Nebulae, silhouetted against a backdrop of glowing gas, is one of the most striking examples of a dark nebulae. The colors of nebulae provide clues about their composition and the processes occurring within them. Red hues often indicate the presence of hydrogen, while greenish tones can signal oxygen emission. Blues and purples typically arise from scattered starlight or ionized helium. Together, these colors create a kaleidoscope of beauty, transforming nebulae into natural works of art. Yet beyond their aesthetic appeal lies a deeper significance. Nebulae are the factories of the universe, producing the elements necessary for life itself. Studying nebulae helps us understand the life cycle of stars and the evolution of galaxies. By observing the formation of protostars and the dispersal of stellar material, scientists gain insights into how solar systems like ours came to be. For instance, the Eagle Nebulae, home to the famous Pillars of Creation, showcases towering columns of gas and dust where new stars are emerging. These structures are sculpted by intense radiation and stellar winds from nearby massive stars, demonstrating the delicate balance between creation and destruction in the cosmos. Nebulae also challenge our imagination, inviting us to ponder the vastness of time and scale. Some nebulae span hundreds of light years, yet their intricate details can only be seen through powerful telescopes. Others, like the Helix Nebula, resemble enormous eyes staring back at us from the depths of space. Each nebula carries the imprint of its history, shaped by the forces of gravity, radiation, and magnetism over millions or even billions of years. For amateur astronomers, nebulae offer some of the most rewarding targets in the night sky. Through binoculars or small telescopes, many nebulae reveal their ghostly forms, shimmering faintly against the backdrop of stars. Astrophotographers spend countless hours capturing their intricate details, using long exposures to bring out the vivid colors hidden to the human eye. These efforts connect us to the wonders of the universe, reminding us that even the faintest glimmers of light carry profound meaning. When we gaze upon nebulae, we're witnessing the ongoing story of the universe, a tale of birth, death, and renewal written in the language of light and matter. They remind us that everything we see, from the air we breathe to the atoms in our bodies, originated in these stellar cauldrons. Nebulae are more than just clouds in space. They are the architects of existence, the places where the ordinary becomes extraordinary. As we continue to explore the cosmos, let us marvel at these star-birthing clouds, whose beauty and complexity inspire both wonder and curiosity. Whether viewed through telescopes or studied via advanced instruments, nebulae invite us to dream bigger, to ask deeper questions, and to embrace the infinite possibilities of the universe. In their swirling mists and radiant hues, we find echoes of our own origins, a reminder that we are part of something far greater than ourselves. Stars, the universe's engines. In the grand tapestry of the cosmos, stars are the threads that hold everything together. These luminous spheres of plasma are more than just distant points of light. They are the engines of the universe, driving the processes that shape galaxies, create elements, and sustain life itself. From their fiery births in nebulae to their dramatic deaths as supernovae or black holes, stars are the beating heart of existence, powering the cycles of creation and destruction that define the cosmos. At their core, stars are fusion reactors, converting hydrogen into helium through nuclear reactions that release unimaginable amounts of energy. This process, known as stellar nucleosynthesis, is the foundation of a star's brilliance. Every photon of light that reaches Earth, from the warmth of our sun to the faint glimmer of distant suns, originates from this alchemy deep within a star's interior. Temperatures at the core of a typical star can exceed 27 million degrees Fahrenheit or 15 million degrees Celsius, hot enough to fuse atomic nuclei and generate the radiation that illuminates the universe. Stars come in a dazzling variety of sizes, colors, and temperatures, each determined by their mass and stage of life. The smallest stars, called red dwarfs, are cooler and dimmer than the sun, burning their fuel slowly and living for trillions of years. In contrast, massive blue giants blaze with ferocious intensity, exhausting their hydrogen reserves in just a few million years before collapsing under their own weight. Our sun, a medium-sized yellow dwarf, strikes a balance between these extremes, providing stable energy that has allowed life on Earth to flourish for billions of years. The life cycle of a star is a story of transformation. It begins in a nebula, where gravity pulls gas and dust into denser clumps. As these protostars grow hotter and denser, they ignite nuclear fusion, marking the start of their main sequence phase, the longest and most stable period of a star's life. During this time, stars like the Sun maintain an equilibrium between the inward pull of gravity and the outward pressure of fusion, shining steadily for billions of years. But no star lives forever. When a star exhausts its hydrogen fuel, it enters the final chapters of its existence. Low and medium-mass stars, like the Sun, swell into red giants as their outer layers expand and cool. Eventually, they shed these layers, leaving behind a dense core known as a white dwarf. High-mass stars meet a more explosive fate, ending their lives in supernovae that outshine entire galaxies for brief moments. These cataclysmic events scatter heavy elements like iron, gold, and uranium across space, enriching the interstellar medium and sowing the seeds for future generations of stars and planets. The remnants of supernovae are equally fascinating. Some collapse into neutron stars, incredibly dense objects with powerful magnetic fields that emit beams of radiation detectable as pulsars. Others form black holes, regions of space-time so warped by gravity that not even light can escape. These enigmatic endpoints of stellar evolution challenge our understanding of physics and offer tantalizing glimpses into the nature of the universe. Stars are also the architects of the periodic table. Through fusion and supernova explosions, they forge the elements essential for life. Hydrogen and helium, the simplest atoms, were created in the Big Bang, but nearly every other element, from the oxygen we breathe to the calcium in our bones, was born inside stars. Carl Sagan famously said, "We are made of star stuff," a poetic reminder that the atoms in our bodies once danced in the fiery hearts of ancient suns. Beyond their role as cosmic factories, stars serve as navigational beacons, cultural symbols, and scientific tools. For millennia, humans have used the positions of stars to chart the seasons, guide voyages, and tell stories. Constellations like Orion, Cassiopeia, and the Southern Cross connect us to our ancestors who looked to the heavens for meaning and direction. Today, astronomers study stars to measure distances across the universe, map the structure of galaxies, and test theories of physics. Variable stars, whose brightness fluctuates over time, act as cosmic yardsticks, helping scientists calculate the scale of the universe. Even the light from stars carries secrets. By analyzing the spectra of starlight, researchers can determine a star's composition, temperature, motion, and age. Doppler shifts reveal whether a star is moving toward or away from us, while subtle wobbles in its position may indicate the presence of orbiting planets. Exoplanet discoveries. many made possible by observing stars, have revolutionized our understanding of planetary systems and raised profound questions about the prevalence of life beyond Earth. Despite their brilliance, stars are not eternal. Their lifespans are dictated by their mass. The more massive a star, the shorter its life. Yet even after they die, their influence endures. Supernova remnants seed the galaxy with the raw materials for new stars, while white dwarfs and neutron stars linger as relics of past eras. Black holes, though invisible, shape their surroundings through gravitational forces, influencing the motion of nearby stars and gas clouds. When we look up at the night sky, we see stars in various stages of their journeys. Some are young and vibrant, others old and fading. Each one tells a story of resilience and change, of forces too vast for human comprehension, yet intimately tied to our existence. Stars remind us that the universe is alive with motion and purpose, driven by processes that transcend individual lifetimes. As we contemplate the stars, let us recognize their dual roles as creators and storytellers. They are the engines that power the cosmos, forging the elements necessary for life and shaping the environments in which planets form. But they are also mirrors reflecting our place in the universe, inviting us to explore, to question, and to marvel at the infinite possibilities of existence. Whether viewed through telescopes, studied via equations, or simply admired on a clear night, stars inspire awe and curiosity, reminding us that even in the vastness of space, there is room for connection, for these celestial engines are part of our shared journey through the stars. Galaxies, cosmic star cities. Stretching across the heavens like sprawling cities of light, galaxies are the ultimate architects of the universe. These colossal structures, composed of billions or even trillions of stars, along with gas, dust, and dark matter, are the building blocks of cosmic organization. Each galaxy is a self-contained ecosystem, teeming with activity and governed by the invisible hand of gravity. From the majestic spirals that swirl like celestial pinwheels to the chaotic jumbles of irregular galaxies, these star-filled metropolises remind us of the grandeur and complexity of the cosmos. At the heart of every galaxy lies a bustling core, often home to a supermassive black hole, millions or billions of times more massive than our sun. These gravitational behemoths anchor their host galaxies, influencing the motion of stars and shaping the environment around them. In some cases, they power quasars, intensely bright jets of energy visible across billions of light-years that serve as lighthouses marking the most distant reaches of the observable universe. The Milky Way, our own galactic home, harbors a supermassive black hole called Sagittarius A star, which quietly resides at its center, occasionally flaring as it consumes nearby material. Galaxies come in a variety of shapes and sizes, each reflecting its unique history and dynamics. Spiral galaxies, like the iconic Andromeda Galaxy and our Milky Way, are among the most visually striking. Their sweeping arms, rich with young stars and glowing nebulae, spiral outward from a dense central bulge. These arms are not static, they're waves of star formation, driven by the rotation of the galaxy and the gravitational pull of its components. As gas clouds compress and collapse within these regions, new stars ignite, creating brilliant clusters that trace the galaxy's structure. Elliptical galaxies, on the other hand, lack the defined shapes of their spiral counterparts. These older, more mature systems appear as diffuse clouds of stars, ranging from nearly spherical to elongated ovals. Ellipticals tend to contain older, redder stars, suggesting that their peak periods of star formation occurred long ago. They often form through mergers, when two or more galaxies collide and merge into a single entity. Over time, the chaotic motions of their stars smooth out, leaving behind a featureless but massive stellar congregation. Irregular galaxies defy classification, their forms shaped by external forces, such as gravitational interactions or collisions with neighboring galaxies. These chaotic assemblies often appear as asymmetrical blobs, filled with bursts of star formation triggered by disturbances in their gas and dust. Despite their messy appearances, irregular galaxies play a crucial role in the cosmic web, acting as reservoirs of raw materials for future generations of stars and planets. The sheer scale of galaxies is almost incomprehensible. The Milky Way spans about 100,000 light-years, or roughly 600 quadrillion miles, yet it is considered an average-sized galaxy. Larger galaxies, such as IC 1101, stretch over 4 million light-years, dwarfing our own. Even smaller dwarf galaxies, though diminutive compared to giants like the Milky Way, contribute significantly to the diversity of the universe. These pint-sized systems often orbit larger galaxies, supplying fresh gas and fueling new rounds of star formation. Galaxies do not exist in isolation. They are interconnected by vast networks of dark matter, forming what astronomers call the cosmic web. Within this web, galaxies cluster together in groups and superclusters, bound by gravity. Our local group, for example, includes the Milky Way, Andromeda, and dozens of smaller satellite galaxies. Over billions of years, these galaxies will continue to interact, with Andromeda expected to collide with the Milky Way in about 4.5 billion years, a slow-motion merger that will reshape both galaxies into a new elliptical form. Collisions and mergers are common in the life cycle of galaxies, driving evolution and transformation. When galaxies collide, their stars rarely crash into one another due to the immense distances between them. Instead, the gravitational forces distort their shapes, triggering waves of star formation and redistributing gas and dust. These events can create stunning phenomena, such as tidal tails, long streams of stars and gas flung outward, and luminous starbursts, where thousands of new stars are born simultaneously. Dark matter plays a pivotal role in the formation and stability of galaxies. Though invisible and detectable only through its gravitational effects, dark matter makes up roughly 85% of a galaxy's mass. It acts as a scaffolding, drawing in ordinary matter and enabling galaxies to form and persist over cosmic timescales. Without dark matter, the delicate balance required for galaxies to exist would collapse, leaving the universe a much emptier place. Studying galaxies provides insights into the origins and fate of the universe itself. By observing distant galaxies, astronomers peer back in time, capturing snapshots of the universe as it was billions of years ago. The farther away a galaxy, the older its light, allowing scientists to reconstruct the history of cosmic expansion and test theories about the Big Bang and dark energy. Instruments like the Hubble Space Telescope and the James Webb Space Telescope have unveiled galaxies so remote that their light has traveled for nearly the entire age of the universe to reach us. Galaxies also serve as laboratories for understanding the interplay between different forms of matter and energy. Active galactic nuclei, or AGN, powered by supermassive black holes, emit intense radiation across the electromagnetic spectrum, offering clues about the physics of extreme environments. Meanwhile, observations of galaxy rotation curves reveal discrepancies between visible matter and gravitational effects, providing some of the strongest evidence for the existence of dark matter. For all their scientific importance, galaxies hold a special place in human culture and imagination. They inspire wonder and humility, reminding us of the vastness of the universe and our tiny but significant role within it. Whether viewed through telescopes or captured in stunning astrophotography, galaxies evoke a sense of connection to the past, to the infinite expanse of space, and to the countless possibilities awaiting discovery. When we gaze upon galaxies, let us marvel at their duality, their ability to be both creators and destroyers, to nurture life while wielding unimaginable power. They are the cosmic star cities, vibrant hubs of activity where the drama of creation unfolds on scales beyond comprehension. Each galaxy carries the echoes of the universe's infancy, the scars of collisions, and the promise of untold stories waiting to be told. And though they may seem impossibly distant, they remind us that we are part of something far greater, a shared journey through the stars, written in the language of light and gravity. The Milky Way, our home galaxy. When we look up at a dark, clear night sky, we often see a faint, milky band of light stretching across the heavens, a celestial river that has inspired myths, guided travelers, and sparked curiosity for millennia. This glowing arc is none other than the Milky Way, our home galaxy, a vast and intricate system of stars, planets, gas, dust, and dark matter that cradles Earth in its embrace. Though it is just one among billions of galaxies in the universe, the Milky Way holds a special place in our hearts and minds because it is where we belong, a cosmic neighborhood teeming with wonder and possibility. The Milky Way is a barred spiral galaxy spanning approximately 100,000 light-years, or about 600 quadrillion miles, from edge to edge. It contains an estimated 100 to 400 billion stars, each one a potential sun with its own planets, moons, and perhaps even life. Our sun resides in one of the galaxy's spiral arms, known as the Orion Arm or Orion Spur, located roughly 27,000 light-years from the galactic center. From this vantage point, we see the Milky Way as a flattened disk, its stars concentrated into a dense, luminous band when viewed from within. At the heart of the Milky Way lies a mysterious and powerful object, a supermassive black hole named Sagittarius A star. With a mass equivalent to about 4 million suns, this gravitational giant anchors the galaxy, influencing the motion of nearby stars and shaping the environment around it. While Sagittarius A star is relatively quiet today, emitting only faint bursts of radiation as it occasionally consumes surrounding material, it serves as a reminder of the immense forces at work in the cosmos. Scientists study this region using radio telescopes and infrared instruments, peering through the thick clouds of dust that obscure the galactic center from visible light observations. The structure of the Milky Way reflects both its beauty and complexity. Its spiral arms are regions of active star formation, where clouds of gas and dust collapse under gravity to create new stellar nurseries. These arms are not rigid structures, but rather density waves, ripples in the distribution of matter that move through the galaxy, compressing material and triggering bursts of starbirth. The Perseus, Sagittarius, and Scutum Centaurus arms are some of the most prominent, each hosting clusters of young hot stars that illuminate their surroundings with brilliant blue and white light. Beyond the spiral arms lies the galactic halo, a sparse and spherical region surrounding the disk. The halo contains ancient stars, globular clusters, and a diffuse haze of dark matter that extends far beyond the visible boundaries of the galaxy. Globular clusters, densely packed groups of hundreds of thousands of stars, orbit the Milky Way like bees around a hive. These clusters are among the oldest objects in the universe, offering clues about the early days of galaxy formation and the conditions that prevailed shortly after the Big Bang. The Milky Way is not static. It is a dynamic and evolving entity. Over billions of years, it has grown through mergers with smaller galaxies, incorporating their stars and dark matter into its own structure. Today, remnants of these past collisions can still be seen in the form of stellar streams, elongated trails of stars torn apart by tidal forces, and dwarf galaxies orbiting on the fringes of the Milky Way. One such satellite, the Sagittarius dwarf spheroidal galaxy, is currently being consumed by our galaxy, its stars gradually assimilated into the larger system. The Milky Way is not static. It is a dynamic and evolving entity. Over billions of years, it has grown through mergers with smaller galaxies, incorporating their stars and dark matter into its own structure. Today, remnants of these past collisions can still be seen in the form of stellar streams, elongated trails of stars torn apart by tidal forces, and dwarf galaxies orbiting on the fringes of the Milky Way. One such satellite, the Sagittarius dwarf spheroidal galaxy, is currently being consumed by our galaxy, its stars gradually assimilated into the larger system. In the distant future, the Milky Way will undergo another dramatic transformation. In about 4.5 billion years, it will collide with its nearest large neighbor, the Andromeda Galaxy. This colossal merger will reshape both galaxies, likely resulting in the formation of a new elliptical galaxy. Despite the scale of this event, individual stars, including our Sun, are unlikely to collide, as the distances between them are vast. Instead, the collision will trigger waves of star formation and redistribute material throughout the newly combined system. Dark matter plays a crucial role in the stability and evolution of the Milky Way. Though invisible and detectable only through its gravitational effects, dark matter accounts for roughly 85% of the galaxy's total mass. It forms a halo that envelops the visible components of the galaxy, providing the gravitational glue needed to hold everything together. Without dark matter, the Milky Way would lose its structural integrity, and its stars would drift away into intergalactic space. For centuries, humans have sought to understand the nature of the Milky Way. Ancient cultures interpreted the glowing band as a heavenly river, a pathway for gods, or a bridge connecting worlds. Modern science has revealed its true identity, a massive, rotating disk of stars and gas orbiting a central core. Yet even with advanced telescopes and sophisticated models, much about the Milky Way remains unknown. How exactly did it form? What lies hidden in its darkest corners? And how common are planetary systems like ours within its vast expanse? Studying the Milky Way offers insights not only into our galaxy, but also into the broader universe. By mapping the positions and motions of stars, astronomers can trace the history of the galaxy's formation and uncover the influence of dark matter. Projects like the European Space Agency's Gaia mission are creating detailed 3D maps of the Milky Way, revealing patterns and structures that were previously invisible. These efforts help us piece together the story of how galaxies evolve over time and how they fit into the larger cosmic web. The Milky Way is more than just a scientific subject. It is a source of inspiration and connection. It reminds us of our place in the universe, a tiny speck within a vast and intricate system. Whether viewed through the lens of a telescope, captured in long-exposure photography, or simply admired on a moonless night, the Milky Way evokes a sense of awe and humility. It challenges us to think beyond ourselves, to embrace the infinite possibilities of existence, and to cherish the fragile oasis we call home. As we explore the Milky Way, let us remember that it is not just a collection of stars and dust. It is a living, breathing entity shaped by the same forces that govern all of creation. It is a testament to the beauty and complexity of the cosmos, a reminder that even in the vastness of space, there is room for connection, for the Milky Way is part of our shared journey through the stars, written in the language of light, gravity, and time. Black holes. Space's dark abyss. In the deepest corners of the universe, where light falters and matter vanishes without a trace, lie some of the most enigmatic and powerful objects known to science. Black holes. These cosmic voids are not empty spaces but regions of extreme density, where gravity's pull is so intense that nothing, not even light, can escape their grasp. Black holes challenge our understanding of physics, warp the fabric of space-time, and serve as gateways to the mysteries of the cosmos. They are the ultimate paradox, invisible yet profoundly influential, silent yet capable of reshaping entire galaxies. At the heart of every black hole lies a singularity, a point of infinite density where the laws of physics as we know them break down. Surrounding the singularity is the event horizon, an invisible boundary that marks the point of no return. Once something crosses this threshold, it is inexorably drawn toward the singularity, stretched and compressed by tidal forces in a process ominously referred to as spaghettification. The event horizon is not a physical surface but rather a mathematical limit, beyond which the escape velocity exceeds the speed of light, a barrier no object can overcome. Black holes come in a variety of sizes, each with its own origin story. Stellar mass black holes form when massive stars collapse under their own weight at the end of their lives. These remnants, typically ranging from a few to tens of times the mass of the Sun, are scattered throughout galaxies like hidden treasures. At the other end of the spectrum are supermassive black holes, behemoths millions or billions of times more massive than the Sun, residing at the centers of most galaxies, including our own Milky Way. Their origins remain a subject of debate, with theories suggesting they may have formed from the mergers of smaller black holes, the direct collapse of massive gas clouds, or the gradual accumulation of material over billions of years. One of the most intriguing aspects of black holes is their ability to shape the environments around them. Supermassive black holes in particular play a pivotal role in galactic evolution. When actively feeding on surrounding gas and dust, they power quasars and active galactic nuclei, or AGN, some of the brightest and most energetic phenomena in the universe. Jets of particles ejected at nearly the speed of light can extend for thousands of light years, influencing star formation and redistributing matter across vast distances. Paradoxically, while black holes consume material, they also regulate the growth of their host galaxies, acting as both creators and destroyers. Despite their fearsome reputation, black holes do not indiscriminately devour everything in their vicinity. Material must first cross the event horizon to be consumed, and many black holes lie dormant for long periods, their presence betrayed only by subtle gravitational effects. Scientists detect black holes indirectly, observing how their immense gravity influences nearby stars and gas. For example, the motion of stars orbiting Sagittarius A star, the supermassive black hole at the center of the Milky Way, provides compelling evidence of its existence. Similarly, X-ray emissions from hot gas spiraling into black holes reveal their locations and properties. The discovery of gravitational waves in 2015 marked a new era in black hole research. These ripples in spacetime, predicted by Albert Einstein's theory of general relativity, occur when massive objects accelerate or collide. In one groundbreaking observation, scientists detected the merger of two stellar mass black holes, each about 30 times the mass of the Sun, as they spiraled together and coalesced into a single larger black hole. This event, which released more energy and gravitational waves than all the stars in the observable universe combined, confirmed the existence of binary black hole systems and opened a new window into the study of these elusive objects. Black holes also push the boundaries of theoretical physics, raising profound questions about the nature of reality. What happens inside a black hole? Is information truly lost forever once it crosses the event horizon, or does it somehow re-emerge elsewhere? These questions lie at the intersection of quantum mechanics and general relativity, two pillars of modern physics that have yet to be fully reconciled. Some physicists propose that black holes may harbor wormholes, hypothetical shortcuts through space-time, or that they could connect to other universes, though such ideas remain speculative. For all their mystery, black holes are not entirely inaccessible. Recent advancements in technology have allowed astronomers to capture the first-ever image of a black hole's shadow, a feat achieved by the Event Horizon Telescope, or EHT, in 2019. By combining data from radio telescopes around the world, the EHT created a virtual Earth-sized observatory capable of resolving the supermassive black hole at the center of the galaxy M87. The resulting image, a glowing ring of light surrounding a dark central void, provided visual confirmation of what was once purely theoretical. It was a moment of triumph for science, affirming humanity's ability to probe the darkest recesses of the cosmos. Black holes inspire both fascination and unease, embodying the unknown and the unknowable. They remind us of the limits of human knowledge while simultaneously driving us to seek answers. Philosophically, they challenge our notions of time, space, and existence. If time slows near a black hole due to intense gravitational fields, what does that mean for observers falling into one? Could black holes represent portals to other dimensions, or are they simply endpoints where the rules of the universe cease to apply? Culturally, black holes have captured the public imagination, appearing in literature, film, and art as symbols of the sublime and the terrifying. From the swirling vortex in Interstellar to the mysterious monoliths in science fiction novels, they evoke a sense of wonder mixed with dread. Yet beyond their dramatic portrayals, black holes are real and tangible, shaping the universe in ways we are only beginning to understand. As we continue to explore these dark abysses, let us embrace the humility they inspire. Black holes remind us that the universe is far stranger and more complex than we can imagine, filled with phenomena that defy explanation. They challenge us to think bigger, to ask harder questions, and to push the boundaries of what we consider possible. Whether studied through telescopes, simulated in computer models, or pondered in philosophical debates, black holes invite us to confront the unknown and marvel at the infinite possibilities of existence. When we contemplate black holes, let us see them not as mere curiosities, but as keystones of cosmic architecture. They are the ultimate test of our ingenuity, the frontier where science meets speculation, and the embodiment of the universe's enduring mysteries. Though they may never reveal all their secrets, black holes remind us that even in the absence of light, there is beauty, and that in seeking to understand the incomprehensible, we find meaning. Quasars, cosmic powerhouses. In the farthest reaches of the universe, where light has traveled for billions of years to reach us, lie some of the most luminous and energetic objects ever discovered, quasars. These brilliant beacons are not stars, nor galaxies in the traditional sense, but rather the blazing hearts of distant galaxies powered by supermassive black holes. Quasars are cosmic powerhouses, emitting energy across the electromagnetic spectrum with an intensity that can outshine entire galaxies. They are relics of a violent and dynamic era in the universe's history, offering a glimpse into the forces that shape the cosmos. At the core of every quasar lies a supermassive black hole, often billions of times more massive than our Sun. Unlike dormant black holes which quietly reside at the centers of galaxies, the black holes in quasars are actively feeding on vast amounts of gas, dust, and stellar material spiraling inward from their surroundings. As this material accelerates toward the event horizon, it forms an accretion disk, a swirling maelstrom of superheated plasma that emits intense radiation. The friction and magnetic fields within the disk generate temperatures so high that they produce light across the spectrum, from radio waves to X-rays, making quasars among the brightest objects in the universe. Quasars are not evenly distributed throughout space. They are predominantly found in the distant universe, their light carrying echoes of a time when the cosmos was young and chaotic. This is no coincidence. Quasars are believed to represent a phase in galactic evolution when supermassive black holes were rapidly growing, fueled by abundant supplies of matter in the early universe. During this epoch, galaxies were still forming, and collisions between them were frequent, funneling gas and dust toward their central black holes and igniting quasar activity. These ancient engines of creation and destruction played a crucial role in shaping the galaxies we see today. The sheer scale of a quasar's energy output is staggering. A single quasar can emit thousands of times more light than the combined output of all the stars in its host galaxy. Some quasars shine with the equivalent brightness of 1 trillion suns, visible across billions of light years. To put this into perspective, if a quasar were placed at the center of our Milky Way, it would outshine everything else in the night sky, casting shadows on Earth despite being located tens of thousands of light years away. Their brilliance makes them invaluable tools for studying the universe, as they serve as lighthouses illuminating the otherwise invisible structures of the cosmos. One of the most remarkable features of quasars is their jets, narrow beams of particles ejected at nearly the speed of light from the vicinity of the black hole. These jets, driven by powerful magnetic fields, extend for millions of light years, carving cavities in the surrounding intergalactic medium and influencing the growth of galaxies. The energy released by quasar jets can heat gas clouds, suppressing star formation in their host galaxies, or trigger bursts of new stars by compressing nearby material. In this way, quasars act as regulators, maintaining a delicate balance between creation and destruction on galactic scales. Despite their immense power, quasars are not eternal. Their activity depends on the availability of fuel, and once the supply of gas and dust dwindles, the quasar dims, leaving behind a quieter, more mature galaxy. This life cycle underscores the transient nature of these cosmic phenomena. They are fleeting moments in the grand narrative of the universe. Yet even after their active phases end, the remnants of quasars continue to influence their environments, shaping the structure and evolution of galaxies over billions of years. Studying quasars presents unique challenges due to their immense distances and extreme conditions. Because their light takes billions of years to reach us, observing quasars is akin to looking back in time, providing snapshots of the universe during its formative stages. Astronomers use telescopes sensitive to different wavelengths of light to study quasars, from radio waves detected by arrays like the Very Large Array or VLA to X-rays captured by space-based observatories such as Chandra and XMM Newton. Spectroscopy allows scientists to analyze the composition, motion, and redshift of quasars, revealing clues about their host galaxies and the expansion of the universe. Quasars also serve as natural laboratories for testing fundamental physics. Their immense gravitational fields warp spacetime, creating gravitational lenses that magnify and distort the light of objects behind them. These lenses enable astronomers to study distant galaxies and supernovae that would otherwise be too faint to observe. Additionally, the variability of quasars changes in their brightness over hours, days, or years, provides insights into the dynamics of accretion disks and the behavior of matter under extreme conditions. For all their scientific importance, quasars evoke a sense of wonder that transcends data and equations. They remind us of the raw power and beauty of the universe, a place where forces beyond human comprehension shape reality on scales unimaginable. Quasars challenge our understanding of black holes, galaxies, and the very fabric of space-time, pushing the boundaries of what we consider possible. They are cosmic paradoxes, beacons of light born from darkness, creators and destroyers, engines of chaos and order. Culturally, quasars inspire awe and curiosity, serving as symbols of the infinite and the unknown. They appear in science fiction as gateways to other dimensions or sources of limitless energy, reflecting humanity's fascination with the mysterious and the extraordinary. Yet beyond their fictional portrayals, quasars are real and tangible, their light-carrying stories written in the language of physics and astronomy. They connect us to the dawn of the universe, reminding us that even the faintest glimmers of light carry profound meaning. As we peer deeper into the cosmos, let us marvel at these cosmic powerhouses, whose brilliance defies imagination and whose influence spans eons. Quasars are more than just astronomical objects. They are messengers from the past, teachers of the present, and guides to the future. Whether studied through telescopes, simulated in computer models, or pondered in philosophical musings, quasars invite us to confront the unknown and embrace the infinite possibilities of existence. In their fiery glow, we find echoes of our own origins, a reminder that we are part of something far greater, a shared journey through the stars, written in the language of light and gravity. Dark matter, the hidden force. In the vast expanse of the universe, much of what we see, the stars, galaxies, and glowing nebulae, represents only a fraction of what truly exists. Beyond the reach of telescopes and the grasp of visible light lies an invisible force that shapes the cosmos, dark matter. This mysterious substance, which neither emits nor reflects light, is the scaffolding upon which the universe is built. Though unseen, its gravitational influence governs the motion of galaxies, the formation of cosmic structures, and the very fabric of space-time itself. Dark matter is the hidden architect of the universe, a silent yet omnipresent force that defies easy explanation. Dark matter makes up about 85% of the total matter in the universe, yet it remains one of the greatest unsolved mysteries in science. Unlike ordinary matter, composed of protons, neutrons, and electrons, dark matter does not interact with electromagnetic forces, rendering it invisible to traditional detection methods. Instead, its presence is inferred through its gravitational effects on visible matter. For example, galaxies rotate faster than they should based on the mass of their stars and gas alone. Without the additional gravitational pull of dark matter, these galaxies would fly apart, their outer regions flung into the void. This discrepancy led astronomers to propose the existence of an unseen form of matter, binding galaxies together like an invisible glue. The evidence for dark matter extends far beyond individual galaxies. On larger scales, it influences the behavior of galaxy clusters, massive assemblies of hundreds or thousands of galaxies bound by gravity. Observations of the Bullet Cluster, a pair of colliding galaxy clusters, provide some of the most compelling proof of dark matter's existence. When these clusters collided, their hot gas clouds slowed down due to friction, while their dark matter components passed through each other unimpeded. By mapping the distribution of mass using gravitational lensing, a phenomenon where light from distant objects is bent by the gravity of intervening matter, scientists were able to separate the locations of ordinary matter and dark matter, revealing the latter's dominant role in shaping the cluster's structure. Despite decades of research, the true nature of dark matter remains elusive. Scientists have proposed several candidates, ranging from exotic particles to primordial black holes, but none have been definitively detected. One leading hypothesis suggests that dark matter consists of weakly interacting massive particles or WIMPs, hypothetical entities that rarely interact with ordinary matter but exert gravitational forces. Experiments deep underground, shielded from cosmic rays and background radiation, are searching for signs of WIMPs colliding with atomic nuclei. Other theories explore alternatives such as axions, sterile neutrinos, or even modifications to our understanding of gravity itself. Each possibility carries profound implications for physics and cosmology, challenging us to rethink the fundamental laws of the universe. Dark matter's influence is not limited to the present day. It played a critical role in the early universe. Shortly after the Big Bang, tiny fluctuations in the density of dark matter created the seeds for the large-scale structure of the cosmos. Over time, these fluctuations grew under the influence of gravity, attracting ordinary matter and forming the first stars, galaxies, and galaxy clusters. Without dark matter, the universe would lack the necessary gravitational scaffolding to assemble these structures, leaving it a diffuse and featureless expanse. In this way, dark matter acts as both a foundation and a catalyst, enabling the rich tapestry of the observable universe to emerge. The quest to understand dark matter has driven technological innovation and interdisciplinary collaboration. Particle physicists, astrophysicists, and cosmologists work together to unravel its secrets, combining data from particle accelerators, space telescopes, and ground-based observatories. Projects like the Large Hadron Collider, or LHC, search for new particles that could explain dark matter, while missions like the James Webb Space Telescope probe the earliest stages of galaxy formation, shedding light on dark matter's role in shaping the universe. Meanwhile, simulations run on supercomputers model the distribution and behavior of dark matter, helping scientists predict its effects and refine their theories. For all its mystery, dark matter inspires both humility and curiosity. It reminds us that the universe is far stranger and more complex than we can imagine, filled with phenomena that challenge our intuition and expand the boundaries of knowledge. Philosophically, dark matter raises profound questions about the nature of reality. What is it made of? How does it interact with the rest of the universe? And why does it dominate over ordinary matter, despite being so elusive? These questions lie at the intersection of science and philosophy, inviting us to ponder the limits of human understanding. Culturally, dark matter has captured the public imagination, appearing in literature, art, and film as a symbol of the unknown and the intangible. Its invisibility and omnipresence evoke a sense of wonder mixed with unease, embodying the tension between what we know and what remains hidden. Yet beyond its symbolic allure, dark matter is a tangible and indispensable part of the cosmos, shaping the environments we inhabit and influencing the trajectories of celestial bodies. As we continue to explore the hidden force that permeates the universe, let us embrace the humility it inspires. Dark matter challenges us to think bigger, to ask harder questions, and to push the boundaries of what we consider possible. Whether studied through cutting-edge experiments, simulated in computer models, or contemplated in philosophical debates, dark matter invites us to confront the unknown and marvel at the infinite possibilities of existence. It is a reminder that even in the absence of light, there is beauty, and that in seeking to understand the incomprehensible, we find meaning. When we contemplate dark matter, let us see it not as an obstacle, but as an opportunity, a gateway to deeper insights into the workings of the universe. It is the ultimate test of our ingenuity, the frontier where science meets speculation, and the embodiment of the cosmos's enduring mysteries. Though it may never reveal all its secrets, dark matter reminds us that even in the shadows, there is truth, and that in striving to uncover it, we illuminate our shared journey through the stars. Dark energy, space's expansion. In the grand theater of the cosmos, one of the most profound and perplexing forces at play is something we cannot see, touch, or directly measure: dark energy. This mysterious entity is responsible for the accelerating expansion of the universe, a discovery that has reshaped our understanding of reality and challenged the very foundations of physics. While dark matter binds galaxies together, dark energy drives them apart, stretching the fabric of space-time and propelling the universe toward an uncertain future. It is the unseen hand that governs the fate of all that exists, a force as enigmatic as it is powerful. The story of dark energy begins with a startling observation made in the late 1990s. Astronomers studying distant supernovae, exploding stars that serve as cosmic mile markers, expected to find evidence that the universe's expansion was slowing down due to the gravitational pull of matter. Instead, they discovered the opposite. The universe was expanding faster over time. This revelation, which earned the Nobel Prize in Physics in 2011, pointed to the existence of a previously unknown force counteracting gravity on cosmic scales. That force was dubbed dark energy, a placeholder term for a phenomenon whose true nature remains elusive. Dark energy accounts for approximately 68% of the total energy content of the universe, making it the dominant force shaping its evolution. Unlike dark matter, which exerts gravitational attraction, dark energy acts as a repulsive force, pushing galaxies away from one another and causing the universe to grow larger at an ever-increasing rate. Its effects are subtle on small scales, but become unmistakable when observing the vast distances between galaxy clusters. Over billions of years, this relentless expansion has transformed the universe from a dense, hot plasma into the sparse, accelerating expanse we see today. One of the leading explanations for dark energy is the cosmological constant, a term introduced by Albert Einstein in his equations of general relativity. Originally conceived as a way to maintain a static universe, a notion later disproven, the cosmological constant now represents the intrinsic energy of empty space itself. According to this theory, even in the absence of matter or radiation, space contains a baseline energy density that drives expansion. However, the calculated value of this energy density differs wildly from predictions based on quantum mechanics, creating what scientists call the cosmological constant problem. This discrepancy highlights the gaps in our understanding and underscores the need for new physics to explain dark energy. Alternative theories propose more dynamic explanations for dark energy. Some suggest it could be a form of quintessence, a hypothetical field that varies over time and space, influencing the rate of expansion differently across the universe. Others explore modifications to Einstein's theory of gravity, suggesting that general relativity may break down on cosmological scales. These ideas remain speculative, but they reflect the creative efforts of scientists to reconcile observations with theoretical frameworks. Each hypothesis carries profound implications, not only for the nature of dark energy, but also for the ultimate destiny of the universe. The implications of dark energy extend far beyond abstract physics. They shape the future of everything we know. If dark energy continues to dominate, the universe will expand indefinitely, growing colder and darker as galaxies drift farther apart. Stars will burn out, leaving behind black holes and dim remnants of once brilliant stellar nurseries. Eventually, even these relics may evaporate through Hawking radiation, leaving behind a vast empty void, a scenario known as heat death. Alternatively, if dark energy grows stronger over time, it could lead to a big rip, tearing apart galaxies, stars, planets, and even atoms themselves. The uncertainty surrounding dark energy leaves open a range of possibilities, each as awe-inspiring as it is sobering. Studying dark energy presents immense challenges due to its intangible nature. Unlike dark matter, which reveals itself through gravitational effects, dark energy operates on scales so vast that detecting its influence requires precise measurements of cosmic phenomena. Scientists rely on tools such as Type Ia supernovae, baryon acoustic oscillations, and the cosmic microwave background to map the universe's expansion history. Projects like the Dark Energy Survey and upcoming missions such as the Nancy Grace Roman Space Telescope aim to refine these measurements, shedding light on the properties of dark energy and testing competing theories. Dark energy also inspires philosophical reflection, challenging our notions of causality, infinity, and the nature of existence. What does it mean for the universe to expand without limit? Is dark energy a fundamental property of space-time, or does it arise from interactions we have yet to understand? These questions blur the line between science and metaphysics, inviting us to ponder the boundaries of human knowledge and the mysteries that lie beyond. Culturally, dark energy captures the imagination as a symbol of the infinite and the unknowable. It appears in literature and art as a metaphor for the inexorable passage of time or the inevitability of change. Its presence reminds us that the universe is not static but dynamic, constantly evolving in ways that defy prediction. Yet beyond its symbolic allure, dark energy is a tangible force, shaping the environments we inhabit and influencing the trajectories of celestial bodies. As we peer deeper into the cosmos, let us marvel at this invisible force that governs the largest scales of existence. Dark energy is more than just a scientific puzzle. It is a reminder of the universe's complexity and our place within it. Whether studied through telescopes, modeled in simulations, or contemplated in philosophical musings, dark energy invites us to confront the unknown and embrace the infinite possibilities of existence. In its quiet, pervasive influence, we find echoes of our own origins, a reminder that we are part of something far greater, a shared journey through the stars, written in the language of light, gravity, and time. When we contemplate dark energy, let us see it not as a barrier but as a frontier, an invitation to explore the deepest mysteries of the universe. It is the ultimate test of our ingenuity, the horizon where science meets speculation, and the embodiment of the cosmos' enduring enigmas. Though it may never reveal all its secrets, dark energy reminds us that even in the vastness of space, there is room for wonder, and that in seeking to understand the incomprehensible, we illuminate our shared journey through the stars. The Big Bang, how it all began. In the beginning, there was nothing, or so it might seem. Yet from this apparent void emerged everything we know: the stars, galaxies, planets, and even the fabric of space and time itself. This momentous event, known as the Big Bang, marks the birth of the universe, a cataclysmic explosion of energy that set the stage for all existence. Though it occurred nearly 13.8 billion years ago, its echoes reverberate through the cosmos today, offering clues to how it all began and what lies ahead. The term Big Bang can be misleading, evoking images of a fiery detonation in space. In reality, the Big Bang wasn't an explosion in the traditional sense, but rather the rapid expansion of space itself. At the instant of the Big Bang, the universe was unimaginably hot and dense, compressed into a singularity, a point of infinite density and temperature where the laws of physics as we know them break down. From this singularity, space and time unfurled, stretching outward in every direction and giving rise to the vast expanse we now call home. In the first fractions of a second after the Big Bang, the universe underwent a period of exponential growth known as cosmic inflation. During this fleeting epoch, which lasted less than a trillionth of a second, the universe expanded faster than the speed of light, smoothing out irregularities and setting the stage for the formation of matter. As inflation ended, the universe cooled, allowing fundamental particles like quarks and electrons to emerge from the primordial soup of energy. These particles soon combined to form protons and neutrons, the building blocks of atomic nuclei. About 380,000 years after the Big Bang, the universe had cooled enough for electrons to bind with protons and neutrons, forming neutral atoms. This pivotal moment, known as recombination, allowed photons, particles of light, to travel freely for the first time. The glow from this era, stretched and redshifted by the universe's expansion, is still detectable today as the cosmic microwave background. Discovered accidentally in 1965 by Arno Penzias and Robert Wilson, the cosmic microwave background serves as a snapshot of the infant universe, revealing subtle fluctuations that seeded the formation of galaxies and large-scale structures. As the universe continued to expand and cool, gravity took center stage, drawing matter together into clumps that would eventually become stars, galaxies, and galaxy clusters. Within these stellar furnaces, nuclear fusion forged heavier elements like carbon, oxygen, and iron, the raw materials necessary for life. Supernovae and neutron star collisions later scattered these elements across the cosmos, enriching the interstellar medium and paving the way for the formation of planets like Earth. In this sense, the Big Bang is not just the origin of the universe, but also the starting point for the intricate web of chemistry and biology that defines our world. The evidence for the Big Bang is overwhelming, drawn from multiple lines of observation. In addition to the cosmic microwave background, scientists have measured the abundance of light elements, such as hydrogen, helium, and lithium, whose ratios match predictions based on the conditions of the early universe. Observations of distant galaxies also show that they are receding from us at speeds proportional to their distance, a phenomenon described by Edwin Hubble in 1929 and explained by the ongoing expansion of space initiated by the Big Bang. Together, these discoveries paint a coherent picture of a universe that began as a single point and has been growing ever since. Yet for all we've learned, many questions remain unanswered. What caused the Big Bang? What existed before it, if anything at all? And why did the universe emerge with the specific properties that allow for complexity in life? These mysteries lie at the intersection of science and philosophy, challenging us to rethink the nature of reality itself. Some theories propose that the Big Bang was not a singular event, but part of a larger multiverse, with countless other universes existing beyond our own. Others suggest that quantum fluctuations or higher dimensional physics may hold the key to understanding the origins of space-time. The Big Bang also raises profound implications for the future of the universe. Depending on the balance between matter, and dark energy, the cosmos could continue expanding indefinitely, leading to a cold, dark fate known as heat death. Alternatively, if gravity eventually overcomes expansion, the universe could collapse back into a singularity in a big crunch, or if dark energy grows stronger, it could trigger a big rip, tearing apart galaxies, stars, and even atoms. Each scenario underscores the fragility and resilience of existence, reminding us that the universe is a dynamic and evolving entity. For all its scientific rigor, the Big Bang inspires awe and wonder, transcending equations and data to touch something deeply human. It reminds us that we are part of a story far greater than ourselves, a narrative written in the language of light, gravity, and time. Whether viewed through telescopes, studied in laboratories, or contemplated in quiet reflection, the Big Bang invites us to embrace the infinite possibilities of existence. It is a reminder that even in the vastness of space, there is room for connection, for the echoes of creation resonate within each of us, binding us to the cosmos in ways both tangible and profound. When we contemplate the Big Bang, let us see it not merely as a historical event, but as a testament to the beauty and complexity of the universe. It is the ultimate origin story, the spark that ignited the stars and set the wheels of creation in motion. Though much remains unknown, the quest to understand the Big Bang drives humanity forward, inspiring us to explore, to question, and to marvel at the infinite wonders of existence. In its fiery beginnings, we find echoes of our own origins, a reminder that we are part of something far greater, a shared journey through the stars, written in the language of light, gravity, and time. Exoplanets. Alien worlds exist. In the vast and uncharted territories of the universe, one of the most thrilling discoveries of modern astronomy is the existence of exoplanets, worlds that orbit stars beyond our sun. These alien worlds, scattered across the galaxy and beyond, have transformed our understanding of the cosmos, challenging long-held assumptions and igniting hope for the possibility of life elsewhere in the universe. From scorching hot Jupiters to icy super-Earths, exoplanets come in a dazzling variety of forms, each offering a glimpse into the boundless creativity of nature. The first confirmed detection of an exoplanet occurred in 1992, when astronomers discovered a trio of rocky planets orbiting a pulsar, a rapidly spinning neutron star. This unexpected find demonstrated that planets could form even in the aftermath of stellar cataclysms. 3 years later, the discovery of 51 Pegasi b, a gas giant orbiting a sun-like star, marked a turning point in exoplanetary science. It was the first exoplanet found around a main sequence star, proving that planetary systems were not unique to our solar neighborhood. Since then, the number of known exoplanets has exploded, with over 5,000 confirmed worlds and thousands more awaiting verification. Exoplanets defy easy categorization, showcasing a diversity that rivals the imagination of science fiction writers. Some are hot Jupiters, massive gas giants that orbit perilously close to their host stars, with surface temperatures exceeding those of molten lava. Others are super-Earths, rocky planets several times the mass of Earth, which may harbor thick atmospheres or subsurface oceans. Then there are the mini-Neptunes, icy or gaseous worlds smaller than Neptune but larger than Earth, whose compositions remain enigmatic. Each type of exoplanet expands our understanding of planetary formation and evolution, revealing the myriad ways in which stars and their companions can coexist. One of the most tantalizing categories of exoplanets is the habitable zone worlds, planets located at just the right distance from their stars to allow liquid water, a key ingredient for life as we know it, to exist on their surfaces. Proxima Centauri b, orbiting the closest star to the Sun, lies within this so-called Goldilocks zone. Similarly, TRAPPIST-1, a diminutive red dwarf star, hosts a system of 7 Earth-sized planets, 3 of which reside in the habitable zone. These discoveries fuel speculation about whether any of these distant worlds might harbor life, sparking dreams of finding extraterrestrial organisms or even intelligent civilizations. Detecting exoplanets is no small feat, given their immense distances and the overwhelming brightness of their host stars. Astronomers employ a variety of ingenious techniques to uncover these hidden worlds. The transit method used by missions like NASA's Kepler and TESS Transiting Exoplanet Survey satellite involves monitoring stars for periodic dips in brightness caused by planets passing in front of them. The radial velocity method measures subtle wobbles in a star's motion induced by the gravitational pull of orbiting planets. Direct imaging, though challenging, captures light reflected or emitted by exoplanets themselves, offering rare glimpses of their atmospheres and surfaces. Together, these methods paint a rich portrait of the exoplanetary landscape. Studying exoplanet atmospheres provides further insights into their potential habitability. Using spectroscopy, scientists analyze the light filtered through an exoplanet's atmosphere during a transit, identifying chemical signatures such as water vapor, oxygen, methane, or carbon dioxide. These molecules serve as clues to the planet's climate, geology, and biological potential. For example, the presence of oxygen and methane together, a combination unlikely to occur without life, could hint at biological activity. While no definitive signs of alien life have been found yet, the search continues with ever more sophisticated tools, including the James Webb Space Telescope, designed to probe deeper into exoplanetary mysteries. Exoplanets also challenge us to rethink the conditions necessary for life. While Earth serves as our primary reference point, the discovery of extremophiles, organisms thriving in Earth's harshest environments, suggests that life might adapt to circumstances far different from those on our home planet. Subsurface oceans on moons like Europa and Enceladus hint at the possibility of life beneath icy crusts, while rogue planets, worlds wandering through interstellar space without a parent star, may retain heat from internal processes, sustaining ecosystems independent of sunlight. The sheer variety of exoplanets expands the scope of where and how life might arise, pushing the boundaries of astrobiology. For all their scientific importance, exoplanets inspire wonder and curiosity, bridging the gap between science and imagination. They appear in literature, film, and art as symbols of exploration and discovery, embodying humanity's yearning to reach beyond the familiar. Yet beyond their cultural allure, exoplanets represent tangible destinations, places we may one day visit or study up close. Advances in technology, from next-generation telescopes to theoretical concepts like interstellar probes, bring us closer to answering age-old questions. What do alien worlds look like? And what can they teach us about our place in the universe? As we continue to explore these alien worlds, let us embrace the humility they inspire. Exoplanets remind us that the universe is far stranger and more diverse than we can imagine, filled with phenomena that challenge our intuition and expand the boundaries of knowledge. They invite us to think bigger, to ask harder questions, and to push the limits of what we consider possible. Whether studied through telescopes, simulated in computer models, or contemplated in philosophical musings, exoplanets connect us to the infinite possibilities of existence. When we contemplate exoplanets, let us see them not merely as distant dots of light, but as gateways to understanding the cosmos. They are the ultimate test of our ingenuity, the frontier where science meets speculation, and the embodiment of the universe's enduring mysteries. Though they may never reveal all their secrets, exoplanets remind us that even in the vastness of space, there is room for wonder, and that in seeking to understand the incomprehensible, we illuminate our shared journey through the stars. Rogue planets, homeless worlds, in the vast and silent expanse of interstellar space, far from the comforting glow of any star, drift solitary wanderers known as rogue planets. These homeless worlds, untethered from the gravitational embrace of a parent star, roam the galaxy like cosmic nomads. Devoid of sunlight and warmth, they exist in perpetual darkness, yet their very existence challenges our understanding of planetary formation and survival. Rogue planets remind us that even in the loneliest corners of the universe, there are stories waiting to be uncovered. Rogue planets defy the traditional definition of a planet, which typically implies an object orbiting a star. Instead, these wandering worlds have been ejected from their birthplaces, perhaps due to gravitational interactions with other planets or stars, or formed independently in regions of dense gas and dust. Some may have originated in protoplanetary disks around young stars, only to be flung into the void during chaotic early stages of system formation. Others might have condensed directly from interstellar clouds, bypassing the need for a stellar nursery altogether. Regardless of their origins, rogue planets represent a population of celestial objects that operate outside the familiar rules of planetary systems. The sheer number of rogue planets is staggering. Estimates suggest there could be billions or even trillions of these lonely worlds scattered throughout the Milky Way, outnumbering stars themselves. Yet detecting them poses immense challenges. Without the reflected light of a nearby star, rogue planets are nearly invisible, detectable only through indirect methods such as gravitational microlensing. This phenomenon occurs when a rogue planet passes in front of a distant star, bending its light due to the curvature of space-time caused by the planet's gravity. For a brief moment, the background star appears brighter, revealing the presence of the otherwise unseen world. Other detection techniques include infrared observations, as rogue planets emit faint heat signatures left over from their formation or generated by internal processes. Life on a rogue planet seems implausible at first glance. Without a host star to provide energy, temperatures plummet to unimaginable lows, often dropping below -200 degrees Celsius, -328 degrees Fahrenheit. Yet scientists speculate that some rogue planets might harbor conditions conducive to life. Subsurface oceans, heated by radioactive decay or residual primordial heat, could shield microbial ecosystems from the harsh cold above. Europa and Enceladus, moons within our own solar system, demonstrate how liquid water can persist beneath icy shells despite frigid surface conditions. If rogue planets possess similar subsurface reservoirs, they could theoretically sustain life forms adapted to extreme environments. The isolation of rogue planets makes them both intriguing and enigmatic. Unlike planets bound to stars, rogue planets experience no day-night cycles, seasons, or tides. Their surfaces are frozen wastelands, battered by cosmic radiation and devoid of sunlight. Yet beneath their icy exteriors, dynamic processes may still unfold. Tectonic activity, driven by internal heat, could shape their hidden landscapes, while atmospheres, if present, might trap trace amounts of warmth, creating fleeting pockets of habitability. These possibilities transform rogue planets from mere curiosities into potential laboratories for studying the resilience of life under extraordinary circumstances. Rogue planets also serve as natural probes of the galaxy's structure and history. As they traverse interstellar space, they carry with them chemical fingerprints of their origins, offering clues about the environments in which they formed. Studying their compositions could reveal insights into the diversity of planetary systems and the mechanisms that govern their evolution. Additionally, rogue planets act as messengers, carrying material across vast distances and potentially seeding new star systems with the building blocks of planets or even life. For all their mystery, rogue planets evoke a sense of melancholy and wonder. They embody the fragility of existence, cast adrift in an indifferent cosmos, yet they also symbolize resilience, surviving against overwhelming odds in the harshest of conditions. Culturally, they capture the imagination as metaphors for solitude, independence, and exploration. Science fiction often portrays rogue planets as mysterious realms hiding ancient secrets or serving as waypoints for interstellar travelers. While these depictions lean toward fantasy, they reflect humanity's fascination with the unknown and our desire to find meaning in the vastness of space. As we peer deeper into the universe, let us marvel at these homeless worlds, whose journeys through the void inspire both humility and curiosity. Rogue planets challenge us to expand our definitions of what constitutes a world, and to consider the myriad ways in which life might adapt to seemingly inhospitable environments. Whether studied through advanced telescopes, modeled in simulations, or contemplated in philosophical musings, rogue planets invite us to confront the unknown and embrace the infinite possibilities of existence. When we contemplate rogue planets, let us see them not as anomalies, but as integral parts of the cosmic tapestry. They are reminders that the universe is far stranger and more diverse than we can imagine, filled with phenomena that defy easy explanation. Though they drift silently through the darkness, rogue planets illuminate fundamental questions about the nature of planets, the origins of life, and our place in the cosmos. In their solitude, we find echoes of our own quest for connection, a shared journey through the stars, written in the language of gravity, time, and endless possibility. Supernovae, stars that explode. In the grand theater of the cosmos, few events rival the dramatic finale of a massive star's life, a supernova. These celestial explosions are among the most powerful and luminous phenomena in the universe, briefly outshining entire galaxies and scattering the raw materials of creation across the void. Supernovae are not merely endings, they are transformative moments that seed the galaxy with elements essential for new stars, planets, and even life itself. They are the ultimate fireworks display, marking the death of one stellar era while paving the way for the next. Supernovae occur in two primary ways, each driven by distinct astrophysical processes. The first type, known as a core collapse supernova, happens when a massive star exhausts its nuclear fuel. Without the outward pressure from fusion to counteract gravity, the star's core collapses under its own weight, triggering a catastrophic rebound. In an instant, the outer layers of the star are blasted into space at speeds approaching 10% of the speed of light, releasing more energy in a few seconds than our sun will emit over its entire 10 billion-year lifetime. This violent explosion leaves behind either a neutron star, a dense remnant composed almost entirely of neutrons, or if the original star was sufficiently massive, a black hole. The second type, called a thermonuclear or type Ia supernova, involves a different kind of stellar demise. These explosions occur in binary star systems where a white dwarf, a remnant of a smaller star, pulls material from a companion star. As the white dwarf accumulates mass beyond a critical threshold, the Chandrasekhar limit, it undergoes a runaway nuclear fusion reaction, igniting carbon and oxygen in its core. The resulting detonation obliterates the white dwarf, leaving no remnant but spreading heavy elements like iron and nickel across vast distances. Because type Ia supernova have consistent peak brightness, they serve as standard candles for measuring cosmic distances, helping astronomers map the expansion of the universe. The aftermath of a supernova is as awe-inspiring as the explosion itself. The ejected material forms a rapidly expanding shell of gas and dust, known as a supernova remnant. Over thousands of years, these remnants interact with the interstellar medium, creating shock waves that compress nearby clouds of gas and trigger the birth of new stars. One of the most famous examples is the Crab Nebula, the remnant of a supernova observed by Chinese astronomers in 1054 AD. At its heart lies a pulsar, a rapidly spinning neutron star emitting beams of radiation that serves as a cosmic lighthouse, flashing with astonishing regularity. Supernovae play a crucial role in the chemical enrichment of the universe. During their explosive deaths, stars forge elements heavier than iron through a process called rapid neutron capture, or the R process. Elements like gold, silver, uranium, and platinum are created in these cataclysmic events, scattered into space to become part of future generations of stars and planets. Every atom of oxygen we breathe, every speck of iron in our blood, and every trace of calcium in our bones owes its existence to the alchemy of supernovae. As Carl Sagan famously said, "We are made of star stuff, and supernovae are the cosmic forges that produce this material." The detection of supernovae has historically been a blend of serendipity and meticulous observation. Ancient civilizations recorded these transient celestial events as guest stars, sudden appearances of bright objects that faded over weeks or months. Modern astronomers use automated surveys and telescopes to monitor thousands of galaxies simultaneously, identifying dozens of supernovae each year. Some of these discoveries have profound implications for cosmology. For example, observations of distant Type Ia supernovae revealed that the universe's expansion is accelerating, a finding attributed to dark energy, one of the greatest mysteries in modern physics. Despite their brilliance, supernovae are fleeting spectacles. Most shine brightly for only a few weeks before fading into obscurity, leaving behind faint remnants that take centuries to evolve. Yet their impact endures. The shock waves from supernovae can compress interstellar gas clouds, initiating the collapse that leads to star formation. Their debris enriches the interstellar medium, providing the building blocks for planets and life. Even the heaviest elements, forged in the intense conditions of a supernova, find their way into the fabric of the universe, connecting us to the ancient and ongoing cycle of stellar evolution. For all their destructive power, supernovae inspire wonder rather than fear. They remind us of the dynamic and ever-changing nature of the cosmos, where destruction and creation are two sides of the same coin. Culturally, they appear in myths and stories as omens, portents, or symbols of transformation. Their brilliance captures the imagination, evoking a sense of awe and humility in the face of forces far greater than ourselves. Yet beyond their symbolic allure, supernovae are tangible phenomena shaping the environments we inhabit and influencing the trajectories of celestial bodies. As we study these stellar explosions, let us embrace the lessons they teach. Supernovae challenge us to think bigger, to ask harder questions, and to push the boundaries of what we consider possible. Whether observed through telescopes, simulated in computer models, or contemplated in philosophical musings, supernovae connect us to the infinite possibilities of existence. In their fiery glow, we find echoes of our own origins, a reminder that we are part of something far greater, a shared journey through the stars, written in the language of light, gravity, and time. When we contemplate supernovae, let us see them not as mere endpoints, but as catalysts for renewal. They are the ultimate test of our ingenuity, the frontier where science meets speculation, and the embodiment of the universe's enduring mysteries. Though they may never reveal all their secrets, supernovae remind us that even in the briefest flashes of light, there is beauty, and that in seeking to understand the incomprehensible, we illuminate our shared journey through the stars. The oldest light in the universe. In the depths of space, beyond the reach of telescopes that probe distant galaxies and stars, lies a faint glow that has journeyed through time and space for nearly 13.8 billion years. This ancient light, known as the cosmic microwave background, CMB, is the oldest radiation in the universe, a relic of the Big Bang itself. It is the afterglow of creation, a snapshot of the universe when it was just 380,000 years old, and it carries within it the imprints of the cosmos' infancy. The CMB is not merely a scientific curiosity. It is a window into the origins of everything we know, a whisper from the dawn of time. The story of the CMB begins with the birth of the universe. In the moments following the Big Bang, the cosmos was an unimaginably hot and dense plasma of particles, photons, and energy. Light could not travel freely through this primordial soup, as it was constantly scattered by free electrons. But as the universe expanded and cooled, protons and electrons combined to form neutral atoms during an era called recombination. For the first time, photons were no longer trapped in constant collisions. They were free to stream across the universe. This moment marked the release of the CMB, a flash of light that has been traveling ever since. Today, the CMB appears as a faint, uniform glow of microwave radiation permeating the entire sky. Its temperature is a frigid 2.7 Kelvin, which is equal to minus 270.45 degrees Celsius, or minus 454.81 degrees Fahrenheit, a remnant of the intense heat of the early universe stretched thin by billions of years of cosmic expansion. Though remarkably uniform, tiny fluctuations, variations on the order of 1 part in 100,000, are embedded within the CMB. These subtle ripples represent slight differences in density, the seeds from which galaxies, stars, and all structure in the universe would eventually grow. The discovery of the CMB in 1965 by Arno Penzias and Robert Wilson was a watershed moment in cosmology. Using a radio antenna originally designed for satellite communications, the two scientists detected an inexplicable hiss of microwave radiation coming from every direction in the sky. Initially dismissed as noise, further investigation revealed that this signal matched predictions made decades earlier by theorists studying the implications of the Big Bang. Their accidental discovery provided compelling evidence for the Big Bang theory and earned them the Nobel Prize in Physics. Since then, our understanding of the CMB has deepened dramatically, thanks to increasingly sophisticated instruments. NASA's Cosmic Background Explorer satellite, launched in 1989, confirmed the CMB's blackbody spectrum and mapped its minute temperature variations, revealing the blueprint of the universe's large-scale structure. Later missions, such as the Wilkinson Microwave Anisotropy Probe and the European Space Agency's Planck satellite, refined these measurements with unprecedented precision. Planck's all-sky map of the CMB, released in 2013, provided a wealth of information about the universe's composition, age, and evolution, confirming that ordinary matter makes up just 5% of the cosmos, while dark matter and dark energy account for the remaining 95%. These temperature fluctuations in the CMB are more than just statistical curiosities. They encode vital clues about the universe's earliest moments. For example, their distribution reveals the geometry of the universe, showing it to be flat on large scales. The patterns also reflect the influence of dark matter, whose gravitational pull shaped the formation of cosmic structures. Additionally, the CMB contains evidence of inflation, a hypothesized period of exponential expansion that occurred in the first fraction of a second after the Big Bang. Tiny quantum fluctuations during inflation were stretched to cosmic scales, leaving behind a fingerprint in the CMB that supports this cornerstone of modern cosmology. Studying the CMB is not without challenges. Its faint signals must be separated from foreground emissions caused by our own galaxy and other astrophysical sources. Yet overcoming these obstacles has yielded profound insights. By analyzing the polarization of CMB photons, how their electromagnetic waves are oriented, scientists have begun to probe the epoch of reionization, when the first stars and galaxies formed, and re-energized the intergalactic medium. Polarization data also holds the potential to detect primordial gravitational waves, ripples in space-time generated during inflation, which would provide direct evidence of this pivotal era. For all its scientific significance, the CMB inspires awe and wonder, transcending equations and data to touch something deeply human. It reminds us that the universe is a dynamic and evolving entity shaped by forces far greater than ourselves. The CMB connects us to the very beginning of time, offering a tangible link to the moment when everything we see, the stars, galaxies, planets, and even life itself, was set into motion. Its presence underscores the interconnectedness of all things, binding us to the cosmos in ways both tangible and profound. Culturally, the CMB captures the imagination as a symbol of eternity and mystery. It appears in art and literature as a metaphor for the infinite and the unknowable, embodying humanity's yearning to understand our place in the universe. Yet beyond its symbolic allure, the CMB is a tangible phenomenon, carrying the echoes of creation within its faint glow. It invites us to confront the unknown and embrace the infinite possibilities of existence. As we peer deeper into the CMB, let us marvel at this ancient light, whose journey through time illuminates the origins of the cosmos. The CMB is more than just a relic of the past. It is a testament to the beauty and complexity of the universe. Whether studied through telescopes, modeled in simulations, or contemplated in philosophical musings, the CMB connects us to the infinite possibilities of existence. When we contemplate the CMB, let us see it not as a mere artifact, but as a living record of the universe's history. It is the ultimate test of our ingenuity, the frontier where science meets speculation, and the embodiment of the cosmos' enduring mysteries. Though it may never reveal all its secrets, the CMB reminds us that even in the faintest glimmers of light, there is beauty, and that in seeking to understand the incomprehensible, we illuminate our shared journey through the stars. Wormholes. Space-time shortcuts. In the realm of theoretical physics, few concepts capture the imagination quite like wormholes, hypothetical tunnels through the fabric of space-time that could connect distant corners of the universe. These cosmic shortcuts, born from the equations of Einstein's general relativity, challenge our understanding of reality and offer tantalizing possibilities for interstellar travel, time exploration, and even glimpses into other universes. Though they remain firmly in the domain of speculation, wormholes inspire wonder and curiosity, embodying humanity's eternal quest to transcend the limits of space and time. The idea of wormholes first emerged from solutions to Einstein's field equations, which describe how matter and energy warp the geometry of space-time. In 1935, Albert Einstein and Nathan Rosen proposed what became known as an Einstein-Rosen bridge, a mathematical construct linking two separate points in space-time. This theoretical structure resembles a tunnel with two mouths connected by a throat, potentially allowing passage between vastly separated regions of the universe or even different universes altogether. While initially considered a mere mathematical curiosity, the concept gained traction as physicists explored its implications for cosmology and quantum mechanics. Wormholes come in various forms, each with unique properties and challenges. The simplest type is a static wormhole, a stable tunnel that remains open indefinitely. However, such wormholes require exotic matter, material with negative energy density, to counteract the gravitational forces that would otherwise collapse the throat. Exotic matter violates classical energy conditions, making it highly speculative and difficult to produce or detect. Without this stabilizing influence, a wormhole would pinch off almost instantly, rendering it useless for practical purposes. Another intriguing possibility is the traversable wormhole, a version stable enough to allow safe passage. Popularized in science fiction as gateways for faster-than-light travel, traversable wormholes raise profound questions about causality and the nature of time. If one end of a wormhole were accelerated to near-light speeds or placed in a strong gravitational field, time dilation effects could create a temporal disparity between its two mouths. This asymmetry might enable backward time travel, raising paradoxes such as the infamous grandfather paradox, where a traveler could theoretically alter their own past. While fascinating, these scenarios remain purely hypothetical, constrained by the laws of physics as we currently understand them. Despite their allure, wormholes face significant scientific and technological hurdles. Even if they exist, creating or sustaining one would demand energies and technologies far beyond anything humanity can achieve today. Some theories suggest that microscopic wormholes may have formed naturally during the early universe, but these would be far too small and unstable to traverse. Others propose that advanced civilizations, if they exist, might harness quantum phenomena or manipulate dark energy to engineer macroscopic wormholes. For now, such ideas belong to the realm of conjecture, fueling both scientific inquiry and creative storytelling. Wormholes also serve as valuable tools for exploring fundamental questions about the universe. They provide a testing ground for theories that attempt to unify general relativity with quantum mechanics, the two pillars of modern physics that have yet to be reconciled. Concepts like string theory and loop quantum gravity incorporate wormholes into their frameworks, suggesting that these structures might play a role in the underlying architecture of space-time. Additionally, wormholes could help explain phenomena such as entanglement, the mysterious connection between particles that appears to transcend spatial separation. Some physicists speculate that entangled particles might be linked by microscopic wormholes, bridging the gap between quantum weirdness and classical physics. For all their theoretical complexity, wormholes resonate deeply with human imagination. They appear in literature, film, and art as symbols of discovery, escape, and transformation. From the iconic Stargate franchise to Christopher Nolan's Interstellar, wormholes capture our longing to explore the unknown and transcend the boundaries of our existence. Yet beyond their cultural appeal, wormholes represent tangible possibilities, inviting us to dream bigger and push the limits of what we consider achievable. As we contemplate these enigmatic structures, let us embrace the humility they inspire. Wormholes remind us that the universe is far stranger and more intricate than we can imagine, filled with phenomena that defy easy explanation. They challenge us to think beyond conventional paradigms, to ask harder questions, and to seek answers in the infinite expanse of knowledge. Whether studied through mathematical models, simulated in computer programs, or pondered in philosophical musings, wormholes connect us to the boundless potential of existence. When we envision wormholes, let us see them not merely as conduits through space and time, but as metaphors for human aspiration. They are reminders that the pursuit of understanding is itself a journey, a shared odyssey through the stars, written in the language of light, gravity, and imagination. Though they may never reveal all their secrets, wormholes inspire us to reach further, to explore deeper, and to marvel at the infinite wonders of the cosmos. In their hypothetical existence, we find echoes of our own quest for connection, a testament to the enduring power of curiosity and the unyielding desire to uncover the mysteries of the universe. Gravitational waves explained. In the vast and silent expanse of the universe, where light and matter often dominate our understanding of reality, there exists a phenomenon that reveals the dynamic nature of space-time itself: gravitational waves. These ripples in the fabric of the cosmos, first predicted by Albert Einstein over a century ago, are echoes of cataclysmic events, collisions of black holes, mergers of neutron stars, and perhaps even the birth of the universe. Gravitational waves are not just scientific curiosities. They are messengers from the most extreme environments in the universe, carrying stories of creation, destruction, and everything in between. The concept of gravitational waves arises from Einstein's theory of general relativity, which redefined our understanding of gravity. According to this theory, massive objects like stars and planets warp the fabric of space-time, much like a bowling ball placed on a stretched rubber sheet creates a depression. When these objects accelerate or collide, they generate disturbances that propagate outward as waves, distorting space-time as they travel. Imagine dropping 2 stones into a still pond. The resulting ripples spreading across the surface are analogous to gravitational waves, except that instead of water, they ripple through the very geometry of space and time. Gravitational waves are incredibly subtle, stretching and squeezing space-time by only the tiniest amounts. For example, the first direct detection of gravitational waves in 2015 by the Laser Interferometer Gravitational Wave Observatory, or LIGO, measured distortions smaller than the width of a proton. This groundbreaking observation confirmed a prediction made by Einstein in 1916 and opened a new era of astronomy known as multi-messenger astrophysics, where scientists study cosmic events using both light and gravitational signals. The waves detected by LIGO originated from the collision of 2 black holes located 1.3 billion light-years away, each about 30 times the mass of the Sun. Their merger released more energy in gravitational waves than all the stars in the observable universe combined, yet the effect on Earth was imperceptible without extraordinarily sensitive instruments. The detection of gravitational waves relies on precision engineering and cutting-edge technology. Instruments like LIGO and its European counterpart, Virgo, use laser interferometry to measure minute changes in distance caused by passing gravitational waves. These detectors consist of 2 perpendicular arms, each several kilometers long, with lasers bouncing back and forth between mirrors at their ends. When a gravitational wave passes through Earth, it causes one arm to stretch while the other compresses, creating an interference pattern that reveals the wave's presence. To filter out noise from seismic activity, thermal fluctuations, and even quantum effects, these observatories employ sophisticated isolation systems and data analysis techniques. Gravitational waves provide unique insights into phenomena that are otherwise invisible or difficult to observe. For instance, the 2017 detection of a neutron star merger, a kilonova, not only confirmed the existence of gravitational waves from such events, but also helped solve long-standing mysteries about the origins of heavy elements like gold and platinum. Observations across multiple wavelengths, including gamma rays, X-rays, and visible light, accompanied the gravitational wave signal, offering a comprehensive view of the event. This marked the first time astronomers could combine electromagnetic and gravitational data to study a cosmic occurrence, revolutionizing our understanding of how the universe works. Beyond their role in astrophysics, gravitational waves challenge us to rethink the fundamental nature of space-time. They probe regimes of gravity far stronger than anything we can create on Earth, testing the limits of general relativity and potentially revealing cracks in our current theories. Some researchers speculate that deviations from Einstein's predictions could point to new physics, such as extra dimensions or modifications to the laws governing gravity. Additionally, primordial gravitational waves, ripples left over from the Big Bang, could provide direct evidence of inflation, the rapid expansion thought to have occurred in the universe's first moments. Detecting these ancient waves remains one of the holy grails of cosmology. For all their scientific importance, gravitational waves evoke a sense of wonder and humility. They remind us that the universe is alive with motion and change, shaped by forces far greater than ourselves. Culturally, they appear in art and literature as symbols of connection and discovery, embodying humanity's yearning to understand the cosmos. Yet beyond their symbolic allure, gravitational waves are tangible phenomena, carrying the imprints of the most violent and transformative events in the universe. They invite us to confront the unknown and embrace the infinite possibilities of existence. As we peer deeper into the ripples of space-time, let us marvel at these cosmic messengers whose journeys span billions of years and unimaginable distances. Gravitational waves are more than just tools for studying the universe. They are reminders of the beauty and complexity of the cosmos. Whether detected through advanced observatories, simulated in computer models, or contemplated in philosophical musings, gravitational waves connect us to the infinite potential of existence. In their faint vibrations, we find echoes of our own origins, a reminder that we are part of something far greater. When we contemplate gravitational waves, let us see them not as abstract concepts, but as living records of the universe's history. They are the ultimate test of our ingenuity, the frontier where science meets speculation, and the embodiment of the cosmos's enduring mysteries. Though they may never reveal all their secrets, gravitational waves remind us that even in the subtlest distortions of space-time, there is beauty, and that in seeking to understand the incomprehensible, we illuminate our shared journey through the stars. The Oort cloud, icy outer shell. At the farthest reaches of our solar system, beyond the orbit of Pluto and the scattered remnants of the Kuiper belt, lies a vast and mysterious region known as the Oort cloud. This distant icy shell encircles the sun like a cosmic cocoon, stretching up to a light-year away, nearly a quarter of the distance to the nearest star. Home to trillions of frozen objects, the Oort cloud is a relic of the solar system's formation, a frozen archive of its earliest days. Though invisible to telescopes, this enigmatic reservoir shapes the comets that occasionally grace our skies and offers clues about the forces that sculpted the planets. The Oort cloud is thought to be a spherical shell of icy bodies, composed primarily of water ice, methane, ammonia, and other volatile compounds. These objects, often referred to as planet symbols, are remnants from the primordial disk of gas and dust that surrounded the young sun over 4.5 billion years ago. As the giant planets formed and migrated during the solar system's chaotic infancy, their gravitational influence scattered countless icy fragments outward, populating the Oort cloud. Today, these ancient relics drift in near isolation, preserved in the deep freeze of interstellar space at temperatures just a few degrees above absolute zero. Despite its immense size, the Oort cloud remains elusive. Its objects are too small, too distant, and too faint to be directly observed with current technology. Instead, scientists infer its existence through indirect evidence, such as the trajectories of long-period comets. These icy wanderers originate in the Oort cloud, dislodged by gravitational nudges from passing stars or molecular clouds. Once set in motion, they embark on journeys that take thousands of years to complete, plunging into the inner solar system before retreating back to their distant home. Comets like Hale-Bopp and Hyakutake, which dazzled skywatchers with their glowing tails, are believed to have originated in this remote reservoir. The structure of the Oort cloud is divided into two regions, an outer spherical shell and an inner, more concentrated disk-like region known as the Hills cloud. The outer Oort cloud extends from roughly 2,000 astronomical units, or AU, where 1 AU is the average distance between Earth and the Sun, to as far as 100,000 AU or more. In contrast, the Hills cloud lies closer to the Sun, overlapping with the outer edges of the Kuiper belt. Together, these regions form a dynamic boundary between the solar system and interstellar space, influenced by both the Sun's gravity and external forces such as galactic tides and stellar encounters. The Oort cloud plays a crucial role in shaping the solar system's dynamics. Its icy inhabitants act as sentinels, preserving chemical signatures from the early solar nebula. By studying comets that originate in the Oort cloud, scientists gain insights into the composition of the protoplanetary disk and the conditions that gave rise to the planets. For example, isotopic analyses of comet materials suggest that some of Earth's water may have been delivered by these icy visitors, highlighting the Oort cloud's potential role in the emergence of life. Beyond its scientific importance, the Oort cloud inspires awe and wonder. It represents the edge of the Sun's gravitational dominion, a boundary where the solar system fades into the vastness of interstellar space. Its sheer scale challenges our intuition, spanning distances so immense that even light takes months or years to traverse them. Yet within this icy expanse lies a profound connection to our cosmic origins. Each object in the Oort cloud carries the imprints of the solar system's birth, frozen in time and space. For all its mystery, the Oort cloud also raises intriguing questions about the broader universe. Could similar structures exist around other stars? What happens when rogue planets or interstellar objects pass through the Oort cloud, disrupting its delicate balance? And what secrets might future missions uncover if humanity ever ventures to explore this distant frontier? While reaching the Oort cloud with current technology would take tens of thousands of years, concepts for advanced propulsion systems offer tantalizing possibilities for probing this icy realm. The Oort cloud captures the imagination as a symbol of the unknown and the infinite. It appears in science fiction as a gateway to uncharted territories, a repository of ancient knowledge, or a barrier separating the solar system from the wider galaxy. Yet beyond its fictional portrayals, the Oort cloud is a tangible part of our cosmic neighborhood, reminding us of the intricate web of forces that govern the universe. It invites us to confront the unknown and embrace the infinite possibilities of existence. As we contemplate the Oort cloud, let us marvel at this icy outer shell, whose silent presence guards the secrets of the solar system's past. It is more than just a collection of frozen objects. It is a testament to the beauty and complexity of the cosmos. Whether studied through cometary observations, modeled in simulations, or pondered in philosophical musings, the Oort cloud connects us to the boundless potential of existence. In its frozen depths, we find echoes of our own origins, a reminder that we are part of something far greater, a shared journey through the stars, written in the language of light, gravity, and time. When we envision the Oort cloud, let us see it not merely as a distant frontier, but as a living record of the solar system's history. It is the ultimate test of our ingenuity, the horizon where science meets speculation, and the embodiment of the cosmos' enduring mysteries. Though it may never reveal all its secrets, the Oort cloud reminds us that even in the coldest and most remote corners of space, there is beauty, and that in seeking to understand the incomprehensible, we illuminate our shared journey through the stars. The Sun's protective bubble. In the vast and often hostile expanse of interstellar space, the Sun provides more than just light and warmth. It creates a protective cocoon that shields our solar system from the harsh realities of the cosmos. This invisible shield, known as the heliosphere, is a dynamic bubble of charged particles and magnetic fields emanating from the Sun. It acts as a barrier against cosmic radiation and high-energy particles from outside the solar system, safeguarding Earth and the other planets within its embrace. The Sun's protective bubble is not just a passive shield, it is a living, breathing structure shaped by the constant interplay between solar winds and the forces of interstellar space. The heliosphere begins at the Sun and extends far beyond the orbit of Pluto, reaching tens of billions of kilometers into space. Its outer boundary, called the heliopause, marks the point where the solar wind, the stream of charged particles emitted by the sun, slows down enough to be overtaken by the interstellar medium, the thin gas and dust that fills the space between stars. Within this boundary lies a region of influence dominated by the sun's magnetic field and plasma, creating a buffer zone that filters out much of the harmful radiation from deep space. The solar wind, which travels at speeds of up to 900 kilometers per second, 560 miles per second, plays a central role in shaping the heliosphere. As it streams outward, it carries with it the sun's magnetic field, forming what scientists call the interplanetary magnetic field. This magnetic field helps deflect charged particles, such as those produced by supernovae or active galactic nuclei, preventing them from penetrating deep into the solar system. Without this protection, Earth's atmosphere would be bombarded by high-energy particles, potentially stripping away ozone layers and exposing life to lethal doses of radiation. The heliosphere is not a static structure, but a dynamic one, constantly responding to changes in the sun's activity. During periods of heightened solar activity, such as solar flares or coronal mass ejections, the solar wind intensifies, temporarily expanding the heliosphere. Conversely, during quieter phases of the sun's 11-year cycle, the heliosphere may contract, allowing more interstellar material to seep closer to the inner solar system. These fluctuations highlight the intricate relationship between the sun and its surroundings, underscoring how the heliosphere serves as both a shield and a mediator between the solar system and the wider galaxy. One of the most intriguing aspects of the heliosphere is its interaction with the interstellar medium. At the heliopause, the solar wind collides with interstellar particles, creating a turbulent boundary layer known as the termination shock. Beyond this point, the solar wind slows dramatically, transitioning into a region called the heliosheath, where the pressure of the interstellar medium compresses and heats the solar wind. Finally, at the heliopause itself, the influence of the sun gives way entirely to the interstellar environment. This boundary was first directly explored by NASA's Voyager 1 and Voyager 2 spacecraft, which crossed into interstellar space in 2012 and 2018, respectively. Their instruments detected dramatic shifts in particle densities and magnetic fields, providing unprecedented insights into the nature of the heliosphere. The heliosphere also plays a crucial role in shaping the habitability of the solar system. By filtering out galactic cosmic rays, high-energy particles accelerated by distant astrophysical events, it reduces the radiation exposure for astronauts, satellites, and even organisms on Earth. For example, studies suggest that prolonged exposure to cosmic rays could increase cancer risks for future Mars explorers, making understanding the heliosphere vital for planning long-term space missions. Additionally, variations in the heliosphere's strength over geological timescales may have influenced the development of life on Earth, offering another layer of connection between the sun's protective bubble and our planet's biosphere. Despite its importance, much about the heliosphere remains unknown. Scientists are still working to understand its exact shape, which appears to be asymmetrical due to the motion of the solar system through the interstellar medium. Some models suggest it resembles a comet-like tail trailing behind the sun, while others propose a more rounded or irregular form. Missions like NASA's Interstellar Boundary Explorer, IBEX, and the upcoming Interstellar Mapping and Acceleration Probe, IMAP, aim to map the heliosphere in greater detail, shedding light on its structure and behavior. For all its scientific complexity, the heliosphere evokes a sense of wonder and gratitude. It reminds us that the sun is not just a source of energy, but a guardian, shielding us from the perils of the universe. Culturally, the heliosphere resonates as a symbol of protection and resilience, embodying humanity's yearning to find safety amidst the vastness of space. Yet beyond its symbolic allure, the heliosphere is a tangible phenomenon, shaping the environments we inhabit and influencing the trajectories of celestial bodies. As we peer deeper into the sun's protective bubble, let us marvel at its elegance and ingenuity. The heliosphere is more than just a shield. It is a testament to the interconnectedness of the solar system and the broader cosmos. Whether studied through spacecraft data, modeled in simulations, or contemplated in philosophical musings, the heliosphere connects us to the infinite potential of existence. In its quiet, pervasive presence, we find echoes of our own origins, a reminder that we are part of something far greater, a shared journey through the stars, written in the language of light, gravity, and time. When we contemplate the heliosphere, let us see it not merely as a physical boundary, but as a living record of the sun's influence. It is the ultimate test of our ingenuity, the frontier where science meets speculation, and the embodiment of the cosmos' enduring mysteries. Though it may never reveal all its secrets, the heliosphere reminds us that even in the subtlest interactions of particles and fields, there is beauty, and that in seeking to understand the incomprehensible, we illuminate our shared journey through the stars. Space weather. Cosmic hazards. The universe is not a static, serene expanse. It is alive with motion, energy, and forces that shape the cosmos in ways both beautiful and perilous. Among these dynamic phenomena lies space weather, a term that refers to the ever-changing conditions in space driven by activity on the sun. From solar flares and coronal mass ejections to geomagnetic storms and radiation belts, space weather represents a hidden yet potent force that can impact life on Earth and beyond. While invisible to the naked eye, these cosmic hazards have the power to disrupt modern technology, endanger astronauts, and even alter the course of human progress. Understanding space weather is not just a scientific endeavor, it is a matter of survival in an increasingly interconnected world. At the heart of space weather lies the sun, a massive ball of plasma whose surface churns with magnetic fields and explosive energy. The sun's outermost layer, the corona, extends millions of miles into space, emitting streams of charged particles known as the solar wind. This constant flow interacts with Earth's magnetic field, creating auroras near the poles and occasionally triggering more severe disturbances. Solar flares are one of the most dramatic manifestations of solar activity. These intense bursts of radiation occur when magnetic energy stored in the sun's atmosphere is suddenly released. A single flare can emit as much energy as billions of nuclear bombs, sending waves of X-rays and ultraviolet light hurtling through space at the speed of light. When directed toward Earth, solar flares can interfere with high-frequency radio communications, disrupt GPS signals, and pose risks to satellites orbiting our planet. Even more formidable are coronal mass ejections, or CMEs, which involve the expulsion of billions of tons of plasma and magnetic fields from the sun's corona. Unlike solar flares, CMEs travel more slowly, taking anywhere from 15 hours to several days to reach Earth, but their effects can be far-reaching. When a CME collides with Earth's magnetosphere, it compresses the magnetic field and injects charged particles into the upper atmosphere. This interaction can lead to geomagnetic storms, which have the potential to wreak havoc on power grids, communication systems, and other critical infrastructure. One of the most infamous examples occurred in March 1989, when a powerful geomagnetic storm caused by a CME knocked out Quebec's power grid, leaving millions without electricity for 9 hours. More recently, in 2012, a massive CME narrowly missed Earth, passing through the planet's orbit just days later. Had it struck, experts estimate it could have caused trillions of dollars in damages and set back technological development for years. Such events underscore the fragility of our reliance on interconnected systems and the urgent need for better forecasting and mitigation strategies. Beyond the immediate impacts of solar storms lie persistent hazards embedded within Earth's own environment. The Van Allen radiation belts, two donut-shaped regions of trapped energetic particles surrounding the planet, serve as reminders of the dangers lurking in space. These belts are filled with high-energy protons and electrons accelerated by interactions between the solar wind and Earth's magnetic field. For astronauts venturing beyond the protective cocoon of Earth's atmosphere, the Van Allen belts present significant challenges. Exposure to such intense radiation increases the risk of cancer, cognitive impairments, and other health issues. Engineers designing spacecraft must incorporate heavy shielding to protect crews, adding weight and complexity to missions. Even robotic satellites operating in these regions face increased wear and tear, shortening their operational lifespans. As humanity sets its sights on returning to the Moon and exploring Mars, understanding and mitigating the effects of radiation will be crucial. Future missions will require innovative solutions, such as advanced materials capable of blocking cosmic rays or pharmaceutical countermeasures to reduce biological damage. In today's digital age, satellites form the backbone of global communication, navigation, and scientific research. Yet these indispensable tools are highly susceptible to the whims of space weather. Solar storms can heat Earth's upper atmosphere, causing it to expand and increase drag on low Earth orbit satellites. This additional resistance can degrade orbits, forcing operators to expend precious fuel reserves to maintain altitude, or worse, result in premature re-entry and destruction. More insidious are the effects of radiation on satellite electronics. High-energy particles can penetrate sensitive components, causing temporary malfunctions or permanent failures. Known as single-event upsets, these glitches can corrupt data, disrupt services, or render entire systems inoperable. For example, in 2003, a series of intense solar storms disrupted over half of NASA's fleet of Earth-observing satellites, highlighting the vulnerability of our orbital infrastructure. To safeguard against these threats, engineers employ techniques like radiation-hardened designs and redundant systems. However, as the number of satellites continues to grow, with tens of thousands planned for deployment in mega-constellations like Starlink, the stakes are higher than ever. A single catastrophic event could cascade into widespread disruptions, affecting everything from internet access to financial transactions. While space weather poses undeniable risks, it also produces some of nature's most breathtaking displays: auroras. These shimmering curtains of light, known as the northern lights and southern lights, occur when charged particles from the sun collide with atoms in Earth's atmosphere. Oxygen molecules glow green or red, while nitrogen emits blue or purple hues, painting the sky with ethereal patterns. Though often celebrated for their beauty, auroras are a reminder of the delicate balance between chaos and order in the cosmos. They represent the visible manifestation of geomagnetic activity, serving as both a warning and a wonder. Indigenous cultures across the Arctic and Antarctic have long revered auroras, weaving them into myths and legends that reflect humanity's enduring fascination with the heavens. Just as meteorologists track hurricanes and tornadoes, scientists monitor space weather using a network of observatories, satellites, and ground-based instruments. Agencies like NOAA's Space Weather Prediction Center and NASA's Solar Dynamics Observatory provide real-time updates on solar activity, enabling governments and industries to prepare for potential impacts. However, predicting space weather remains a formidable challenge. Unlike terrestrial weather, which unfolds over hours or days, solar phenomena can evolve rapidly, leaving little time for response. Moreover, the sun's behavior is inherently chaotic, governed by complex interactions between magnetic fields, plasma, and gravity. Despite advances in modeling and observation, accurately forecasting the timing and intensity of solar storms remains elusive. Efforts are underway to improve prediction capabilities, including the development of next-generation telescopes and machine learning algorithms. By analyzing vast data sets collected from past events, researchers hope to identify patterns and precursors that could enhance early warning systems. Such innovations will be essential as humanity ventures deeper into space and becomes increasingly dependent on satellite-based technologies. Addressing the hazards posed by space weather requires a multifaceted approach. On Earth, governments and utilities are investing in technologies to harden power grids against geomagnetic storms. Transformers equipped with surge protectors and backup systems can help mitigate the impact of geomagnetically induced currents, reducing the likelihood of prolonged outages. Similarly, Telecommunications companies are developing protocols to reroute signals during periods of heightened solar activity, ensuring continuity of service. In space, advancements in materials science and engineering are paving the way for more resilient satellites. Lightweight composites and radiation-resistant coatings offer enhanced protection without compromising performance. Meanwhile, international collaborations aim to establish guidelines for responsible space operations, minimizing the risk of cascading failures in crowded orbits. Education and public awareness also play vital roles in preparing society for space weather events. By fostering a culture of readiness, communities can respond effectively to disruptions, whether they involve loss of power, degraded communications, or compromised navigation systems. Space weather serves as a poignant reminder of humanity's place in the grand tapestry of the cosmos. We are not passive observers, but active participants in a dynamic relationship with the sun and the wider universe. As we continue to explore and utilize space, we must acknowledge both its wonders and its perils. The quest to understand and adapt to space weather reflects our innate curiosity and resilience. It challenges us to think creatively, work collaboratively, and embrace uncertainty. Whether through groundbreaking discoveries, technological innovations, or philosophical reflections, space weather invites us to confront the unknown and embrace the infinite possibilities of existence. In the end, the story of space weather is not just about cosmic hazards, it is about connection. It reminds us that we are part of something far greater, bound together by the same forces that shape stars, planets, and galaxies. And as we peer into the swirling maelstrom of the sun's fury, we find echoes of our own origins, a testament to the enduring power of curiosity and the unyielding desire to uncover the mysteries of the universe. Magnetars, magnetic monsters. In the darkest corners of the universe, where gravity reigns supreme and light struggles to escape, lie some of the most extreme objects known to science, magnetars. These enigmatic stellar remnants are not just remnants of dead stars, they are cosmic powerhouses, wielding magnetic fields so intense that they defy comprehension. A magnetar's magnetic field can be 1 trillion times stronger than Earth's, capable of erasing credit cards from millions of miles away and warping space-time itself. They are the ultimate paradox, small enough to fit within a city, yet powerful enough to influence vast regions of space. Magnetars challenge our understanding of physics, pushing the boundaries of what we consider possible and offering a glimpse into the raw forces that govern the cosmos. Magnetars belong to a family of objects known as neutron stars, the dense cores left behind after massive stars explode as supernovae. Neutron stars themselves are extraordinary. Imagine compressing the mass of the sun into a sphere just 12 miles across, creating an object so dense that a teaspoon of its material would weigh billions of tons. But magnetars take this already extreme scenario to another level. What sets them apart is their magnetic field, which is thousands of times stronger than those of typical neutron stars. This colossal magnetism arises during their formation when rapid rotation and violent collapse amplify magnetic flux lines, locking immense energy into their tiny frames. The origins of magnetars are tied to the deaths of the most massive stars in the universe. When a star many times the mass of the sun exhausts its nuclear fuel, it collapses under its own gravity, triggering a supernova explosion. If the core that remains is between 1.4 and 3 solar masses, it becomes a neutron star. In rare cases, however, conditions align to create a magnetar. Scientists believe these conditions include exceptionally fast rotation and highly turbulent environments during the star's final moments. The result is a neutron star with a magnetic field so strong that it distorts atomic structures and generates exotic states of matter. To grasp the sheer scale of a magnetar's magnetic field, consider this: Earth's magnetic field measures about 0.25 to 0.65 Gauss at its surface. By comparison, a refrigerator magnet produces around 50 Gauss. A typical neutron star might have a magnetic field of 10 to the power of 12 Gauss, but a magnetar's field can reach up to 10 to the power of 15 Gauss, enough to strip electrons from atoms and disrupt molecular bonds over astronomical distances. At such intensities, even empty space behaves strangely. The quantum vacuum, normally a void devoid of particles, can become polarized, leading to bizarre effects like photon splitting and altered light propagation. Magnetars are laboratories for testing the limits of physics, where the rules governing matter and energy are stretched to their breaking points. Despite their diminutive size, magnetars wield catastrophic power. Their magnetic fields store enormous amounts of energy, which can be released in sudden, violent outbursts. These eruptions manifest as gamma-ray bursts, X-ray flares, and radio pulses detectable across vast distances. One of the most famous events associated with magnetars occurred on 27th of December 2004, when a burst of gamma rays from a magnetar called SGR 1806-20 swept through the solar system. The blast was so powerful that it disrupted Earth's ionosphere, despite originating from a magnetar located 50,000 light-years away. For a brief moment, it became one of the brightest objects in the sky, outshining entire galaxies. Such events highlight the destructive potential of magnetars, whose fury can ripple through space and time, leaving lasting imprints on their surroundings. These outbursts are thought to occur when a magnetar's crust, a solid layer made of densely packed neutrons, experiences starquakes. Imagine the entire surface of the star shifting and cracking due to the immense stresses imposed by its magnetic field. These quakes release tremendous amounts of energy, propelling jets of particles and radiation into space. Some of these emissions travel at nearly the speed of light, carrying clues about the magnetar's internal structure and the nature of its magnetic field. Observing these phenomena allows scientists to probe the inner workings of these mysterious objects, shedding light on the behavior of matter under conditions unattainable in terrestrial laboratories. The discovery of magnetars began in the late 20th century, thanks to advances in X-ray and gamma-ray astronomy. Early observations revealed strange sources emitting periodic bursts of high-energy radiation. These sources were dubbed soft gamma repeaters, SGRs, and anomalous X-ray pulsars, AXPs, terms that reflected their unusual properties. Over time, researchers realized that both classes shared common characteristics, including slow spin rates and incredibly strong magnetic fields. This realization led to the unification of SGRs and AXPs under the umbrella term magnetars, providing a framework for understanding their behavior. One of the defining features of magnetars is their rapid spin-down rate. Unlike other neutron stars, which maintain relatively stable rotation periods, magnetars lose angular momentum quickly due to the braking effect of their magnetic fields. This slowdown is accompanied by a gradual weakening of the magnetic field over thousands of years, eventually transforming the magnetar into a more ordinary neutron star. However, while active, magnetars remain among the most energetic objects in the universe, capable of producing phenomena that dwarf anything seen on Earth or even in nearby stars. Magnetars also play a crucial role in shaping our understanding of the universe. Their outbursts provide valuable insights into the processes that govern high-energy astrophysics. For example, studying the radiation emitted during magnetar flares helps scientists refine models of particle acceleration, plasma dynamics, and magnetic reconnection, the process by which magnetic field lines snap and reconnect, releasing stored energy. These mechanisms operate not only in magnetars, but also in other astrophysical contexts, such as solar flares and black hole accretion disks. By observing magnetars, researchers gain a deeper appreciation for the fundamental forces that drive cosmic activity. Moreover, magnetars offer tantalizing hints about the nature of dark matter and the early universe. Some theories suggest that primordial magnetars, formed shortly after the Big Bang, could serve as seeds for supermassive black holes, explaining how these giants grew so quickly in the young universe. Others propose that interactions between magnetars and dark matter could produce observable signatures, such as gravitational waves or anomalous radiation patterns. While speculative, these ideas underscore the importance of magnetars as tools for exploring some of the deepest mysteries in cosmology. For all their scientific significance, magnetars evoke a sense of awe and wonder. They remind us of the raw power and beauty of the universe, a place where forces far beyond human comprehension shape reality on scales unimaginable. Culturally, magnetars capture the imagination as symbols of extremes and transformation. They appear in literature and art as harbingers of doom or sources of limitless energy, reflecting humanity's fascination with the unknown and the extraordinary. Yet beyond their fictional portrayals, magnetars are real and tangible, their light and radiation carrying stories written in the language of physics and astronomy. They connect us to the dawn of the universe, reminding us that even the faintest glimmers of light carry profound meaning. As we peer deeper into the cosmos, let us marvel at these magnetic monsters whose brilliance defies imagination and whose influence spans eons. Magnetars are more than just astronomical phenomena. They are messengers from the past, teachers of the present, and guides to the future. Whether studied through telescopes, simulated in computer models, or contemplated in philosophical musings, magnetars invite us to confront the unknown and embrace the infinite possibilities of existence. When we contemplate magnetars, let us see them not as anomalies, but as integral parts of the cosmic tapestry. They are reminders that the universe is far stranger and more diverse than we can imagine, filled with phenomena that defy easy explanation. Though they may never reveal all their secrets, magnetars inspire us to reach further, to explore deeper, and to marvel at the infinite wonders of the cosmos. In their hypothetical existence, we find echoes of our own quest for connection, a testament to the enduring power of curiosity and the unyielding desire to uncover the mysteries of the universe. The story of magnetars is ultimately one of resilience and discovery. From their violent births to their cataclysmic outbursts, these magnetic monsters embody the dynamic and ever-changing nature of the cosmos. They challenge us to think bigger, ask harder questions, and push the limits of what we consider achievable. Whether observed through cutting-edge instruments, modeled in simulations, or pondered in quiet reflection, magnetars connect us to the boundless potential of existence. In their quiet, pervasive presence, we find echoes of our own origins, a reminder that we are part of something far greater, a shared odyssey through the stars, written in the language of light, gravity, and imagination. And so, as we are coming to the end of this video, let us remember that magnetars are not merely distant curiosities. They are living records of the forces that shape the cosmos, silent witnesses to the birth and death of stars, and guardians of secrets waiting to be uncovered. Each observation brings us closer to understanding their mysteries, yet each answer often raises new questions. Magnetars embody humanity's enduring quest for knowledge, challenging us to think bigger, ask harder questions, and seek answers in the infinite expanse of space. In the end, the story of magnetars is not just about magnetic fields and neutron stars, it is about connection. It reminds us that we are part of something far greater, bound together by the same forces that shape stars, planets, and galaxies. And as we peer into the swirling maelstrom of their fury, we find echoes of our own origins, a testament to the enduring power of curiosity and the unyielding desire to uncover the mysteries of the universe. If you're eager to explore more of the universe's astonishing wonders, join us by subscribing and sharing your thoughts in the comments. Your questions and insights help guide our next journey. If this video sparked your curiosity, a thumbs up goes a long way in helping others discover the marvels of space. Thank you for being part of this adventure. May these facts about the vast cosmic expanse that cradles our home inspire you to keep looking up and wondering.